Why the laws of physics can never break. What if I told you that the laws of physics have never been broken? Not in the searing, crushing heart of a black hole. Not even in the first, impossible moment of the Big Bang. Now, we've all been taught to think of these places as cosmic dead ends, where the universe's rulebook gets torn to shreds and our equations just scream, infinity, at us. But that's an illusion. It's a grand and beautiful illusion. The truth is, the very things we think are breaking the universe are actually showing us, with breathtaking clarity, how it all really works. The laws aren't breaking. Our understanding is expanding. And in that expansion, we find a universe far more profound and far more elegant than we ever dared to imagine. Welcome to the Science for Deep Sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. We see it in headlines all the time. At the center of a black hole, the laws of physics break down. It's a dramatic, captivating idea. It conjures up images of reality itself tearing at the seams. And, in a way, it's true. The equations we use, the trusted tools that predict the orbits of planets and the behavior of light, they do fail. They give us answers of infinite density and infinitely curved spacetime numbers that are, for all practical purposes, nonsense. The same thing happens when we try to rewind the cosmic clock to the very first instant of the Big Bang. We hit a wall, a point our physics can't describe, what we call a singularity. It feels like a failure. It feels like the end of the line for logic. But it's not. It is, in fact, the exact opposite. These moments aren't the universe breaking its own rules. They're the universe telling us that our rulebook is incomplete. And this isn't the first time it's happened. The history of science is just the story of us discovering the edges of our knowledge and bravely stepping beyond them. The Newtonian break, our first great illusion. For over 200 years, the universe seemed to run like clockwork, the clockwork of Isaac Newton. In the late 17th century, Newton gave us a set of laws for motion and gravity that were so powerful, so precise, they seemed to be the final word from the cosmos. These weren't just abstract ideas, they were practical tools that built the modern world. With Newton's equations, we could predict the path of a cannonball, the return of a comet, and eventually, chart a course to the moon. Newton gave us a universe that was tidy and predictable. If you knew where everything was and how it was moving, you could, in theory, calculate the entire future and past of the cosmos. For centuries, this was our reality. The laws were perfect. But by the late 19th century, tiny cracks started to appear in this perfect facade. They were subtle, almost insignificant, but they refused to be ignored. The first was a flicker of light. Newtonian physics says speeds should just add up. If you're on a train going 100 kilometers per hour and throw a ball at 20, someone on the ground sees it moving at 120. Simple. But light didn't play by these rules. Experiments showed something baffling. The speed of light in a vacuum was constant, no matter how fast you were moving. This was a direct contradiction. It was as if you turned on a flashlight on that train, and both you and the observer on the ground measured the light beam moving at the exact same speed. It made no sense. It was a break. The second crack was a wobble in the heavens. The planet Mercury was misbehaving. Its orbit wasn't the perfect, repeating ellipse Newton's laws predicted. The orbit itself was slowly rotating. Astronomers were meticulous. They accounted for the gravitational pull of every other planet. Still, there was a tiny discrepancy, a shift of just 43 arcseconds per century that they couldn't explain. They even proposed a hidden planet, Vulcan, between Mercury and the Sun. They searched for decades and found nothing. Newton's laws, the bedrock of physics, were failing in our own backyard. Did this mean Newton was wrong? Did his laws, break? Not at all. And this is the crucial point. A young patent clerk in Bern, Switzerland, named Albert Einstein, offered a new perspective. He took the experimental results seriously, especially that constant speed of light. He asked, what must be true about the universe for light's speed to be the same for everyone? His answer was the theory of special relativity. It revealed that space and time weren't a rigid background like Newton thought. They were woven into a single, flexible fabric, space-time. And this fabric could stretch and shrink. As you approach the speed of light, time for you slows down, and your length contracts, from the perspective of someone standing still. This was a radical idea, but it perfectly explained why light's speed is constant. It wasn't that Newton's laws were broken. It was that they were a brilliant, incredibly accurate approximation that works flawlessly in the slow speed, weak gravity world we live in. Driving a car, flying a plane, even launching a rocket all happen at a tiny fraction of light speed. In that zone, Newton's equations are more than good enough. It's like using a flat map to navigate a city. The map is technically wrong. The Earth is a sphere, but for that small scale, it works perfectly and is much simpler than a globe. Newton's laws are our flat map of the cosmos. They aren't wrong. They're just incomplete. 10 years later, in 1915, Einstein's general theory of relativity took it further. He proposed that gravity wasn't a mysterious force, but the result of mass and energy warping space-time. The sun creates a deep dent in space-time, and planets are just following the straightest path through that curve. This new understanding not only explained everything Newton's laws did, but it also perfectly predicted Mercury's strange wobble. So, did Newton's physics break? No. It was revealed to be a special case of a deeper truth. This is our first lesson. When a law seems to break, it's a sign that we're using the wrong map for the territory. The universe is fine. We just need to zoom out. The quantum break, when reality gets weird. Just as the world of the very fast forced us to rethink Newton, exploring the world of the very small demanded an even more radical shift. At the turn of the 20th century, physicists peered into the atom, and what they found was a realm so bizarre, so contrary to our intuition, that it made relativity look tame. In this quantum world, the familiar laws of classical physics didn't just bend, they shattered. Take an electron. In our world, we imagine it as a tiny ball with a definite position and momentum. The quantum world scoffs at this. It says that before we measure it, the electron doesn't have a definite position. It exists as a superposition of all possible positions at once, a cloud of probability described by a wave function. Only when we measure it does this wave collapse, and the particle snaps to a single location. This is wave-particle duality. Sometimes quantum objects act like particles, and other times they act like waves. The classic double-slit experiment shows this perfectly. Fire electrons one by one at two slits, and you don't get two bands on the screen behind. You get an interference pattern, as if each electron went through both slits at once as a wave and interfered with itself. How can something be in two places at once? It seems to break logic itself. This leads to the famous Heisenberg uncertainty principle. It states there's a fundamental limit to how precisely we can know certain pairs of properties, like position and momentum. Many people think this is just a measurement problem that our clumsy tools jostle the particle. But the uncertainty is an intrinsic feature of reality. A particle does not possess a perfectly defined position and momentum at the same time. It's not that we can't know them, it's that they don't exist in the way we think they should. So, here again, it looks like a break. The predictable world of Newton evaporates into a fog of probability. But once more, this is an illusion born from our everyday expectations. The laws of physics haven't broken. We've just found a new, more fundamental set of laws. Quantum mechanics is the foundation of classical physics. So why don't we see a baseball act like a wave and go through two doors at once? Because for large objects, the quantum effects are so unimaginably small they become completely negligible. The baseball's wave function is so tightly focused that for all practical purposes, Newton's laws describe its path perfectly. Classical mechanics emerges from quantum mechanics at large scales, just as Newtonian physics emerges from relativity at low speeds. The quantum break was the discovery of the universe's hidden, probabilistic operating system. The broken rules of the classical world were just a simplified instruction set. The black hole break, gravity's grandest stage. With general relativity, we had a powerful new theory of gravity. But hidden in Einstein's own equations was a prediction so monstrous that even he couldn't believe it was real. The equations predicted that an object could be so massive and dense that it would warp space-time to a breaking point, creating a region from which nothing, not even light, could escape. They predicted the black hole. For decades, many, including Einstein, thought it was just a mathematical quirk. But then we found them. We saw stars orbiting empty space, detected X-rays from matter being torn apart, and eventually, took a direct picture of a black hole's silhouette. They're real. And this is where physics supposedly faces its most dramatic test. General relativity predicts that all the matter in a black hole gets crushed into a point of zero volume and infinite density, the gravitational singularity. Here, space-time's curvature becomes infinite, and the equations of general relativity, built on smooth space-time, just stop working. They give us infinity, which is math's way of saying, I have no idea. Nobel laureate Kip Thorne famously described the singularity as the point where all laws of physics break down. But let's look closer. Is it really the asterisk universe's laws breaking, or just our theory? General relativity does a spectacular job describing the black hole from the outside. The breakdown happens at a single, unseeable point hidden deep inside. Think back to the map analogy. At the center of a black hole, our map has a tiny hole in it that says, "Here be dragons." But does that mean the territory itself has a hole in it? Or just our map? The singularity isn't a sign of lawlessness. It's a giant, flashing neon sign telling us where our understanding ends. It's the one place where the two pillars of modern physics, general relativity, the theory of the very big, and quantum mechanics, the theory of the very small, must finally meet. The singularity is what happens when a theory of the smooth and continuous, relativity, tries to describe a reality that is likely granular and quantum. Of course it fails. The breakdown isn't an end. It's the most powerful clue we have that there must be a deeper theory, a theory of quantum gravity that can unite them. Such a theory would likely do away with the idea of an infinite point, resolving the singularity and mending the break. The black hole isn't where physics dies. It's the crucible where the next generation of physics is being forged. The ultimate frontier. The Big Bang and quantum gravity. If a black hole's singularity is a signpost to a new physics, the Big Bang is the ultimate destination. When we run the clock backward, everything in the universe rushes together until, about 13.8 billion years ago, we hit the same problem. Our equations lead us to an initial singularity, a moment when the entire universe was apparently a point of zero volume with infinite density and temperature. This seems to be the most fundamental failure of all. But by now, you know the pattern. This failure is the exact same kind we saw inside a black hole. It's a clash between general relativity and quantum mechanics. The initial singularity is not a physical object. It's an admission from our current theories that they are out of their depth. It is the universe telling us, you need a theory of quantum gravity to understand this. The search for this theory is the single greatest challenge in modern physics. There are several candidates. String theory proposes that everything is made of tiny, vibrating strings of energy, with different vibrations appearing as different particles. In some versions, the Big Bang singularity is replaced by a big bounce from a previous universe. Another approach, loop quantum gravity, suggests that spacetime itself is made of discrete atoms of space and time. You can't squeeze the universe down to zero volume if there's a minimum possible size. Again, the singularity vanishes. These theories are still being developed and are incredibly hard to test. But the key takeaway is that physicists don't actually believe the universe began from a point of infinite density. They see the singularity as a known bug in our current models, a placeholder for a future, more complete description. Each break isn't a defeat. It's a discovery. It's a map to buried treasure, revealing that the rules we thought were fundamental were just bylaws for our corner of the cosmos. The goal of physics is to find the single, unbroken thread from which the entire tapestry is woven. An elegant universe. We've journeyed from Newton's clockwork solar system to the quantum realm's probabilistic haze, and stared into the abyss of a black hole and the dawn of time. In every case, the story is the same. What first looks like a catastrophic breakdown of physical law is actually a moment of revelation. Newton's laws weren't broken. They were shown to be an approximation of Einstein's relativity. Classical mechanics wasn't broken. It emerges from the deeper rules of quantum mechanics. And general relativity isn't truly broken by singularities. Those points of infinity are just signposts pointing us toward a theory of quantum gravity. The laws of physics, the true, underlying rules, don't break. They can't. They're the operating system of reality. It's our knowledge, our human-written user manuals, that are incomplete and need updating. These breaks are the most exciting moments in science because they signal we're on the verge of a profound leap. They show us that the universe isn't chaotic at its extremes, but is governed by a deeper, more elegant set of principles than we yet comprehend. The illusion is the breaking. The reality is the expansion of our knowledge. And the prize is a deeper connection to the stunning, consistent, and ultimately knowable universe we are lucky to be a part of. Exploring these ideas is what science is all about, pushing our knowledge to the absolute edge and daring to peek over. If you enjoyed this journey to the frontiers of physics, consider subscribing and joining our community of curious minds. The universe is full of mysteries, and together, we can try to unravel them. The one law of reality that is truly unbreakable: you throw a ball into the air, you just know it's coming back down. It always does. You can track its arc, guess where it'll land, and you trust its journey with an almost religious certainty. We see that same certainty everywhere. A rocket, a triumph of engineering, screams toward the heavens, its every move governed by principles we can scribble on a blackboard. This is how we experience the universe. As a place with rules, a cosmos run by an invisible, but totally reliable, code. We call them the laws of physics, and we think of them as the rigid, unbending statutes of existence. Break them, and the universe itself would fall apart. But is that really right? We tend to think of the laws of physics as this strict, cosmic rulebook, a set of commands that simply can't be broken. But what if that's the wrong way to look at it? What if, instead of a rulebook, the laws of physics are more like a map? A map of the terrain of existence. This isn't just a clever word game, it's a total shift in perspective, and it changes everything. On this journey, you'll see why you can't just violate the map, and what really happens when we try. We're going to the very edge of our understanding, to the places where our maps run out. And we'll be forced to confront the one law that might truly be unbreakable, because it isn't a law at all, it's the architecture of reality itself. The illusion of the cosmic rulebook. For most of our history, the idea of a cosmic rulebook wasn't an illusion. It was a revolutionary breakthrough. Before the scientific age, the world felt random and unpredictable, governed by mysterious forces and moody deities. The planets traced a divine dance, a lightning strike was a sign of anger, and a falling rock was anyone's guess. Then, in the 17th century, Isaac Newton changed the game. With just a handful of elegant equations, he seemed to have found God's own instruction manual for the universe. His laws of motion and universal gravitation were stunning in their power. An object at rest stays at rest. Force equals mass times acceleration. For every action, an equal and opposite reaction. Suddenly, the same rules that explained an apple falling in an English orchard could also chart the majestic, clockwork orbits of the planets. It was a revelation. For the first time, humanity felt like it could actually read the mind of the cosmos. This Newtonian view cemented the idea of physical laws as prescriptive. They were like cosmic statutes, commands etched into the fabric of creation that every atom had to obey. The universe was a grand machine, and Newton had handed us the schematics. This way of thinking was incredibly successful. Armed with this rulebook, we built the modern world. We engineered bridges, launched satellites, and sent astronauts to the moon, all by following Newton's rules with absolute faith. The laws just worked. Every single time. They felt eternal and perfect. But the universe is a little more subtle than any rulebook we could write. As our tools got more precise, tiny cracks started to show up in Newton's perfect edifice. At first, they were just whispers. Astronomers noticed that the orbit of Mercury wasn't behaving quite like Newton's laws predicted. It wobbled. Its elliptical path around the Sun slowly rotated, or precessed, by a tiny amount, just 43 arcseconds per century more than could be explained by the pull of the other planets. It was a minor issue, almost a rounding error, but it wouldn't go away. For decades, scientists tried to explain it by hypothesizing a hidden planet, which they even named Vulcan, hiding between Mercury and the Sun. But Vulcan was never found. At the other end of the scale, a different puzzle popped up around light. James Clerk Maxwell's work in the 19th century showed that light was an electromagnetic wave that traveled at a very specific, constant speed, c. But according to Newton, speeds should always be relative. If you're in a car going 50 miles per hour and you throw a ball forward at 10, someone on the sidewalk sees the ball moving at 60. That's just common sense. But light refused to play by these rules. It didn't matter how fast you were moving towards a beam of light or away from it, you would always measure its speed to be the exact same value, c. These weren't violations of a cosmic law. Nobody was getting sent to physicist jail. These were clues that our understanding, our rulebook, wasn't the final word. It was like we had a map of our local town that was perfect for getting to the store, but it fell apart when we tried to use it to navigate to another continent. It didn't mean the town had broken the rules of the map. It just meant the map was incomplete. The world was bigger and weirder than our map had led us to believe. The illusion of a perfect rulebook was shattering, making way for a new idea. Physics isn't a set of rules, but a description of a landscape we're still exploring. From rules to descriptions. The map of reality. When Albert Einstein arrived on the scene in the early 20th century, he didn't just add a new page to the rulebook. He threw the book out and gave us a whole new kind of map. With his theories of special and general relativity, Einstein redrew our entire picture of the universe. Take Mercury's wobbling orbit. The solution wasn't a hidden planet. Einstein's idea was way more radical. He proposed that gravity isn't a force at all, not some invisible rope pulling things together, like Newton thought. Instead, gravity is a feature of the universe's geometry. He said that mass and energy actually warp the fabric of space and time, creating curves and dips in the cosmic landscape. Planets orbit the Sun not because they're being pulled, but because they're following the straightest possible path through this curved space-time, like a marble rolling inside a bowl. When you calculate Mercury's path through the deep curve in spacetime near the Sun, its weird wobble is predicted with perfect accuracy. The anomaly was gone. This is the huge shift from a prescriptive law to a descriptive one. Newton's law said, "An object shall be pulled by gravity." It was a command. Einstein's theory says, spacetime is curved by mass, and objects just follow the curves. It's a description. A statement of fact about the terrain. You can't violate the shape of the terrain. You can only move through it. The ball you throw comes back down not because it's obeying a rule, but because the Earth's mass has created a big dent in spacetime, and the ball is just following the curve of that dent back down. This reframing applies to all of physics. The laws aren't divine edicts. They're summaries of patterns we've seen, crafted through a non-stop cycle of observation, hypothesis, and experiment. They're the language we invented to describe the consistent way the universe behaves. When scientists say, "An object in motion stays in motion," they aren't giving an order. They're summarizing countless observations of how things act. Think of it like this. A speed limit 50 inches sign is a asterisk prescriptive law. It's a rule we impose, and you can break it. But a traffic engineer's report that says, "The average speed on this highway is 65 inches" is a asterisk descriptive law. It's a summary of what's actually happening. If you drive by at 40, you haven't violated the description. You've just given the engineer a new data point. For centuries, we treated the laws of physics like speed limit signs. Einstein taught us they're more like the engineer's report. When relativity superseded Newton, it didn't prove Newton wrong. It just gave us a better map, one that worked not just in our slow-moving local neighborhood but also on the cosmic highways where things get fast and gravity gets intense. In fact, if you use Einstein's equations for slow speeds and weak gravity, they simplify right back down to Newton's. Newton's map is still a perfectly good approximation for its limited domain. This is both humbling and exciting. It means our knowledge is never finished. Our maps can always get better. We aren't just subjects living under cosmic tyranny. We're active explorers, cartographers of reality, constantly refining our maps. But this brings up a deeper question. If these laws are just our descriptions, are they real? Are we just inventing useful labels for patterns, or are we uncovering something fundamental about the universe's structure? Are we just describing traffic flow, or are we finding the architecture of the highway itself? This question forces us to look for the unyielding foundation that lies beneath it all. The unbreakable foundation. Inviolable structures. To tackle that question, we need to draw a line between the descriptive rules we've been talking about and what we might call inviolable structures. Descriptive rules are our maps, Newton's laws, the laws of thermodynamics. They're breakable only in the sense that our description might be incomplete. When we find a new phenomenon, like Mercury's orbit, we're forced to redraw our map to create a more comprehensive one, like Einstein's. The rule isn't broken. Our understanding just got bigger. Inviolable structures are something else. They aren't the map, they're the terrain itself. They aren't rules on the game of reality. They're the code that defines what the game is. You can't break these structures for the same reason you can't walk off the edge of a video game map, not because a rule says you can't, but because the game's code literally doesn't include anything beyond that boundary. The edge is the limit. Let's look at the most famous of these structures, the speed of light. In sci-fi, starship captains are always trying to break the light barrier. But this is a basic misunderstanding of what c is. The speed of light is not a cosmic speed limit sign. It's a fundamental, structural property of spacetime itself. More accurately, it's the speed of causality. It's the maximum speed at which any cause can travel to create an effect. It's the universe's ultimate transfer rate for information. Why? Think of the universe as a simulation running on a cosmic computer. The speed of light is like the processing speed of that computer. It's the fastest rate one pixel can affect another. It's not a rule in the game, it's a hardware limitation of the game. Going faster than light would be like asking the game to process something before its own clock allows it to happen. It's a logical contradiction. The consequences are mind-bending. If you could outrun causality, you could get a reply to a message before you sent it. You could see an effect before its cause. The entire logical flow of time past, present, and future would collapse. The universe would stop making sense. This is why you can never accelerate a particle with mass to the speed of light. As it gets closer, its relativistic mass increases, and the energy needed to speed it up any more approaches infinity. At particle accelerators like CERN, protons are pushed to 999,999% the speed of light, but they never, ever cross that final barrier. They are tracing the absolute boundary of the game. Other fundamental laws are better understood as these kinds of inviolable structures. Take the asterisk conservation of energy. It states energy can't be created or destroyed. This isn't just a good idea, it's a reflection of a deep symmetry of the universe. The brilliant mathematician M.E. Noether proved that for every continuous symmetry in nature, there's a conserved quantity. Energy is conserved because the laws of physics themselves don't change over time, they are symmetric through time. To violate energy conservation would mean the fundamental workings of the universe could change from moment to moment. Now, a few controversial studies have suggested that some fundamental constants might have shifted slightly over cosmic history, which would imply this symmetry isn't absolutely perfect. But for all practical purposes, this principle is cosmic bedrock. Then there's the second law of thermodynamics the law of increasing entropy. It's not just that disorder always increases. It's a statistical law. It says systems tend to go from less probable states to more probable states. An egg unscrambling itself isn't technically impossible, just so fantastically unlikely that it's like all the air molecules in your room deciding to hang out in one corner. There are just vastly more ways for things to be disordered than ordered. This statistical certainty gives us the arrow of time. We remember the past, low entropy, but not the future, high entropy. While this holds true on any scale that matters to us, physicists are always pushing the boundaries. Recent research has shown that in tiny, bizarrely correlated quantum systems, this principle can get a little weird, suggesting quantum effects can create tiny loopholes at the atomic scale. But in our macroscopic world, trying to reverse entropy would be like trying to reverse the flow of time itself. These aren't rules that reality consults. They are its foundational properties. And that's why they are unbreakable. You can't break the frame that reality is built on. You can only discover its shape. Some physicists even suspect that all these inviolable structures might emerge from one, even deeper principle that defines spacetime itself. The edge of the map. So what happens when we push physics to its absolute breaking point? To places where gravity is so intense and energy so high that our current understanding just falls apart. These places are real. They exist at the heart of a black hole, and at the very beginning of time. When a giant star dies, its core can collapse into a black hole. According to Einstein's theory, at the center is a singularity, a point of zero volume and infinite density, where the curvature of spacetime becomes infinite. At this point, the equations of general relativity, our best map of gravity, simply break. They spit out answers like infinity, which is the universe's way of telling us our map is no longer valid here. Likewise, if we rewind the cosmic clock back to the Big Bang, general relativity predicts an initial singularity, a moment of infinite temperature and infinite density. Once again, our map gives us an infinity and goes silent. Does this mean reality itself is breaking? No. This is the key. A singularity in our theory doesn't mean reality is broken. It means our map is broken. We've reached the edge of the known world, the "here be dragons" on the chart of our understanding. General relativity is our brilliant map of the big stuff, stars and galaxies. Quantum mechanics is our equally brilliant map of the tiny stuff, atoms and particles. The problem is, in a black hole or the Big Bang, you have the realm of relativity, immense mass, crushed into the realm of quantum mechanics, an infinitesimally small space. Our two maps contradict each other here. This is the frontier. The hunt for a theory of quantum gravity, like string theory or loop quantum gravity, is the quest for a new map that works everywhere. These theories are today's explorers trying to chart those unknown lands. They're trying to draw a map that doesn't have an infinity at its center, but instead describes the quantum fabric of spacetime itself. And even these futuristic theories don't offer ways to break the fundamental structures. A theory of quantum gravity won't give us a faster-than-light travel loophole. Instead, it will explain why these structures are the way they are from an even deeper level. It will likely show us that the inviolable structures we've seen emerge from the collective behavior of the fundamental atoms of spacetime. So when we face a singularity, we're not seeing an exception. We're getting an invitation, a challenge to discover a deeper layer of reality. The laws don't break us. The asterisk limits of our laws break us, forcing us to grow, to explore, and to draw a better map of this magnificent terrain. This journey into the nature of reality is exactly what we love to explore on this channel. It's a journey of questioning, discovery, and standing in awe of the cosmos. If you find these deep dives into the universe's biggest questions as fascinating as I do, consider subscribing and joining our community of fellow explorers. Now I have to ask, what other law of physics feels truly unbreakable to you? Let me know in the comments below, and maybe we can tackle it on a future journey together. So where does that leave us? We started with a simple idea. The universe follows rules, like a giant machine following a schematic. But we've seen that's not the whole story. The laws of physics aren't a rigid rulebook, but a living map, a set of descriptions that we, as cosmic cartographers, are constantly refining. We saw that what looks like breaking a law is actually a moment of discovery, a clue that our map isn't big enough. Then, we pushed deeper and found that beneath our evolving maps lies the fundamental terrain, the inviolable structures of existence itself. Things like the conservation of energy and the arrow of time aren't rules to be followed. They're deep symmetries and statistical certainties woven into the fabric of what is. And at the heart of it all, we found the best candidate for the title of the truly unbreakable law: the speed of light. Not a speed limit, but the speed of causality, a structural boundary that defines the very meaning of cause and effect. It can't be broken because it isn't a rule on reality. It is a fundamental property of reality. So, the next time you switch on a light, remember what you're seeing. That beam of light isn't just obeying a law. It's defining the game we're all playing. It's revealing a piece of the universe's fundamental code. And we, in our endless curiosity, are just beginning to figure out how to read it. What happens at the absolute edge of reality? What if you could take a trip to the very edge of reality? I don't just mean the edge of the observable universe. I mean the conceptual boundary of existence itself. A place where the laws of physics, the fundamental rules that build our world, are stretched to their absolute breaking point, yet somehow, they refuse to shatter. It sounds like something out of science fiction, but these edges are very real. They're woven into the fabric of the cosmos, defining what's possible and what will forever be just beyond our reach. So today, we're going on a journey to two of the most extreme locations imaginable. The event horizon of a black hole, the ultimate edge of gravity and speed, and the coldest possible point in the cosmos, the unattainable state of absolute zero. Along the way, we'll find a third, even more fundamental limit: the fuzzy, uncertain nature of reality at its very smallest scales. We're going to explore what happens at these extremes, where our understanding of space, time, and matter is pushed to the max. But more importantly, we'll ask why these limits even exist. We'll discover how these unbreakable rules aren't cosmic killjoys, but the essential guardrails that keep our entire universe from spiraling into chaos. These aren't just limitations, they're the pillars holding reality together. The edge of gravity. The event horizon. Our first stop is maybe the most mythologized object in the entire universe: a black hole. But we're not diving into the monster itself. We're traveling to its doorstep, a boundary more profound and bizarre than any physical wall. We're going to the event horizon. To get what an event horizon is, you first have to understand the universe's ultimate speed limit. Picture this. You're in the fastest spaceship ever built, trying to race a single beam of light. You pour every last drop of energy into your engines, pushing harder and harder. But no matter how fast you go, that beam of light still pulls away from you at exactly 299, 792, 458 meters per second. It's like the universe itself is telling you, nope, that's it. This isn't just a technological problem, it's a fundamental law. Thanks to Einstein's theory of relativity, we know that as an object with mass gets closer to the speed of light, its mass effectively increases. The energy needed to speed it up grows exponentially, until at the speed of light, you'd need an infinite amount of energy. So, nothing with mass can ever get there. Photons, the particles of light, can only travel this fast because they're massless. They don't just obey the speed limit, they're the speed limit. We see this every day in our most powerful particle accelerators. We can slam protons together at 999,999% of the speed of light, but no matter how much power we pump in, they never, ever cross that final barrier. This cosmic speed limit is the key to the event horizon. A black hole is an object so incredibly dense that its gravitational pull becomes immense. Eventually, you reach a point where the escape velocity, the speed you need to break free from its gravity, is faster than the speed of light. Since nothing can go faster than light, nothing can escape. The event horizon isn't a physical surface you could touch. It's an invisible line in space-time that marks the point of no return. Once you cross it, the laws of physics have one simple, brutal message: you can never go home. The trip to this boundary is where things get really weird, and it all depends on your point of view. Let's imagine you're on a spaceship, watching your brave or maybe foolish friend fly toward a supermassive black hole. From your safe distance, you'd see one of the strangest effects in all of physics: gravitational time dilation. The black hole's immense gravity warps spacetime, and that literally slows down the flow of time. From your perspective, the closer your friend gets to the event horizon, the slower their clock appears to tick. At first, it's a tiny difference. But as they get right up to the edge, the distortion becomes extreme. You'd see their ship seem to slow to a crawl. The light from their ship would get stretched out by gravity, shifting toward the red end of the spectrum in what's called gravitational redshift. They would appear dimmer and redder, their movements becoming agonizingly slow. Finally, as they reached the event horizon, their image would seem to freeze completely. To you, they would be stuck in time at the edge of the abyss, fading over an eternity until their light was redshifted into nothing. From your perspective, they would never, ever cross. But for your friend, the one actually taking the plunge, their experience is totally different. For them, time flows just fine. There's no big barrier, no dramatic moment when they cross the event horizon. They just float across that invisible line, completely unaware they'd just passed the point of no return. Looking back, they might see the entire future of the outside universe play out in a cosmic fast-forward. While crossing the line might be anticlimactic, the journey onward is anything but. As your friend gets closer to the singularity at the center, the infinitely dense point where all the mass is crushed, they'd experience a grim process called spaghettification. The gravitational pull on their feet, being just a tiny bit closer to the singularity, would be exponentially stronger than the pull on their head. This difference, a tidal force, would stretch their body longer and thinner, like a piece of spaghetti, until they were torn apart atom by atom. Inside the event horizon, the rules of reality itself get rewritten. The roles of space and time actually switch. In our normal lives, we can move anywhere in space, forward, backward, left, right, but we're always pushed forward in time. Inside a black hole, that's reversed. The singularity is no longer a asterisk place in space, it's an asterisk event in time. It becomes the future. Just like you and I are constantly moving toward next Tuesday, anything that crosses the event horizon is moving toward the singularity. Every possible path, no matter which way you turn, leads only to the center. Escape is impossible, not because you don't have a strong enough engine, but because out is no longer a direction. It's in your past. You're trapped not by gravity, but by the very geometry of a reality that has been twisted beyond all recognition. The edge of cold, absolute zero. All right, after surviving our trip to the edge of gravity, we're heading to another, equally profound boundary. The absolute edge of cold. This isn't just a chilly day in Antarctica or the vacuum of deep space. We're going to a temperature so low it represents a fundamental limit of the cosmos. Absolute zero. Absolute zero is 0 Kelvin, which is a frosty minus 273, 15 degrees Celsius, or minus 459, 67 degrees Fahrenheit. We usually think of temperature as heat, but it's really a measure of motion, the kinetic energy of atoms and molecules vibrating and zipping around. The hotter something is, the more its particles are jiggling. In classical terms, absolute zero is the theoretical point where all of that motion completely stops. The particles would be perfectly still, holding no heat energy at all. It's the ultimate state of chill, a point of perfect calm. But here's the catch. You can never actually get there. The third law of thermodynamics is very clear on this. It's impossible for any process to reach absolute zero in a finite number of steps. Think of it like this. You're trying to walk to a wall by first covering half the distance, then half of the asterisk remaining distance, and so on. You'll get infinitely close, but you'll never actually touch the wall. Cooling something down works the same way. You use a fridge to remove some heat, and it gets colder. You use a more advanced method to remove more heat, and it gets colder still. But with each step, it gets exponentially harder to remove the tiny bit of heat that's left. Reaching absolute zero would require an infinite number of cooling stages, which is physically impossible. Scientists have gotten ridiculously close, though. Using techniques like laser cooling, where they use lasers to literally nudge atoms and slow them down, researchers have hit temperatures of just 38 picokelvin. That's 38 trillionths of a degree above absolute zero. But they can never, ever close that final, infinitesimal gap. So why not? Why does the universe forbid this perfect stillness? The answer comes from the wonderfully weird world of quantum mechanics. At the smallest scales, the universe isn't neat and tidy, it's fuzzy and probabilistic. This is summed up in one of physics' most important ideas, the Heisenberg uncertainty principle. It states that you can't simultaneously know both a particle's exact position and its exact momentum. And it's not because our tools aren't good enough, it's a fundamental feature of reality. The more precisely you pin down a particle's location, the less you know about where it's going, and vice versa. So, if a particle reached absolute zero, its motion would stop, and its momentum would be precisely zero. If it was perfectly still, you could also know its exact position. You'd know both its position and its momentum with perfect certainty. And that would flat out violate the uncertainty principle. The universe just doesn't allow it. Because of this quantum rule, particles can never be perfectly still. Even at their lowest possible energy state, they have to hold on to a tiny bit of motion called zero-point energy. This isn't heat you can remove. It's a fundamental quantum jitter, an inherent vibration baked into spacetime itself that can never be silenced. This is why liquid helium, for instance, will never freeze solid under normal pressure, no matter how cold it gets. Its zero-point energy is just enough to keep its atoms from locking into place. Even though we can't reach absolute zero, the journey toward it reveals some of the most bizarre and fascinating stuff in the universe. At these ultra-cold temperatures, the individual particles were used to start behaving according to the strange rules of quantum mechanics on a massive scale. One of the most mind-blowing examples is the Bose-Einstein condensate. First created in a lab in 1995, this is a state of matter that forms just billionths of a degree above absolute zero. At this temperature, the atoms get so cold and slow that their quantum waves overlap. They essentially lose their individual identities and begin to act as a single, massive quantum entity, a superatom. Thousands or even millions of atoms merge into one coherent quantum wave, all behaving in perfect unison. It's quantum mechanics you can see. This leads to things like superfluidity and superconductivity. Cool liquid helium down below about 2 Kelvin, and it becomes a superfluid, a liquid that flows with zero friction. It can crawl up the walls of its container, seemingly defying gravity. A vortex in a superfluid will spin forever without slowing down. Similarly, some materials, when cooled way down, become superconductors, letting electricity flow with zero resistance. A current started in a superconducting loop could theoretically flow forever, no power source needed. These strange states aren't just lab tricks. They're a direct result of the universe's ultimate cold limit. They show us what happens when the quantum world, usually hidden away at the subatomic level, bleeds into our reality. The edge of cold isn't an edge of nothingness. It's an edge where the rules of the game change completely. The edge of knowledge. The quantum realm. We've journeyed to the edge of spacetime at the event horizon and to the edge of energy at absolute zero. But there's a third, even more fundamental edge to reality that's been hiding underneath both of them. It's not a place you can go to, but a limit on what you can ever know. This is the edge defined by quantum uncertainty. As we saw with absolute zero, the Heisenberg uncertainty principle is a cornerstone of physics. It puts a fundamental trade-off into the universe between certain pairs of properties, like position and momentum. Think of it like trying to take a picture of a speeding car. If you use a super-fast shutter speed to get a sharp image of its position, the photo will be so crisp it's just a blur, you won't know how fast it was going. If you use a slow shutter speed to capture the motion blur and figure out its speed, you lose any sense of its exact location. The huge insight of quantum mechanics is that this isn't a problem with your camera. It's a property of the car itself. A quantum particle, like an electron, doesn't have a precise position and a precise momentum at the same time. Its existence is better described as a wave of probability, a probability cloud, where it's more or less likely to be found. This inherent fuzziness is woven into the very fabric of reality. This might sound like a frustrating limitation, like the universe is hiding the details from us. But this principle isn't a flaw, it's a critical feature. It's a guardrail that keeps our universe stable. Think about a simple atom. If an electron could have a precise position and zero momentum, what would stop it from being pulled into the positively charged nucleus? Atoms would collapse in an instant. The universe as we know it with stable matter, chemistry, and life simply couldn't exist. The uncertainty principle prevents this collapse. By forcing a particle to have some uncertainty in its momentum, it guarantees a minimum amount of energy, that same zero-point energy we ran into earlier. This quantum jitter keeps the electron from falling into the nucleus, ensuring the stability of every atom in the cosmos. And this rule isn't just for tiny things, it has shaped the entire universe. The Big Bang Theory says our universe started in an incredibly hot, dense state. And when we look at the afterglow of the Big Bang, the cosmic microwave background, it's almost perfectly uniform. Almost. There are tiny temperature fluctuations, about 1 part in 100,000. These little imperfections are the fossilized imprints of quantum fluctuations from the first moments of time. In that primordial soup, the uncertainty principle meant that energy couldn't be perfectly smooth. There were tiny, random quantum jitters that created pockets of slightly higher or lower density. Then, during a period of rapid expansion called inflation, these microscopic fluctuations were stretched to astronomical scales. Those slightly denser regions became the seeds of all cosmic structure. Over billions of years, gravity pulled more matter into them, forming the vast web of galaxies, stars, and planets we see today. Every structure in our universe, including our galaxy and ourselves, owes its existence to the fundamental uncertainty that was present at the dawn of time. In a very real sense, we are the macroscopic results of a subatomic roll of the dice. This edge of knowledge even touches on our first destination, the black hole. Quantum mechanics says that even empty space is a fizzing sea of virtual particles that pop into existence and then annihilate each other in an instant. But right at the event horizon, something amazing can happen. A pair of particles can be created right on the edge. One might fall in, but the other escapes. To an outside observer, it looks like the black hole is emitting radiation. This is the famous Hawking radiation. Over unimaginable timescales, this process causes the black hole to lose mass and, eventually, evaporate completely. The ultimate prison is undone by the universe's fuzziest rule. The edge of gravity is ultimately governed by the edge of quantum uncertainty. This journey to the edges of reality shows us a universe bound by incredible, unbreakable rules. Pushing our understanding right up to those boundaries is the very essence of science. If this kind of cosmic exploration gets your mind racing, consider subscribing to the channel. We're always venturing into the unknown, and we'd love for you to join us. So, what's the takeaway from our grand tour of reality's edges? We've journeyed to the event horizon, where space and time swap places. We've peered over the edge of absolute zero, a state of perfect cold that's forever out of reach. And we've seen that the very foundation of our universe is built not on certainty, but on a fundamental, unavoidable fuzziness. We've learned that these limits the speed of light, the impossibility of absolute zero, the principle of uncertainty aren't arbitrary roadblocks. They are deeply connected laws that form the logical bedrock of the cosmos. They are the guardrails that keep reality from unraveling. Just imagine for a second a universe without these rules. If you could travel faster than light, you could create all sorts of paradoxes, arriving somewhere before you even left. If you could reach absolute zero, you could break the fundamental laws of energy and time. If there were no quantum uncertainty, atoms would collapse, and the universe would be a boring, structureless soup. Our universe doesn't work that way. The rules hold firm. But they aren't a cage. They are the very canvas on which reality is painted. The laws of physics work together to create a universe that is consistent, stable, and, maybe most importantly, comprehensible. The universe thrives not in spite of its rules, but because of them. And the most beautiful part is that knowing these boundaries doesn't stop us from exploring. In fact, it inspires us. It's at these extreme edges in the warped space-time around a black hole, in the bizarre quantum states near absolute zero, and in the probabilistic dance of subatomic particles that we find the deepest clues to how reality works. The limits of our universe define the playground for our curiosity, and there is still so much to discover within its incredible, unbreakable bounds. The glitch inside every black hole. At the heart of every single black hole, our understanding of the universe just crashes. The laws of physics, the very rulebook for the cosmos, seems to break down at an infinitely dense, infinitely small point called a singularity. But what if this isn't a bug? What if it's a feature? A glitch that actually reveals the source code of reality itself, connecting the biggest things in the universe to the smallest quantum jitters. This isn't a story about an error. It's a story about a clue, a breadcrumb trail leading from the crushing darkness of a black hole to the true nature of everything. We've been told that in these places, physics fails. But the truth is far more interesting. Where the old laws hit their limits, new, deeper laws are just waiting to be found. So today, let's go hunt for that glitch. We're going to decode the message hidden at the center of a black hole, a message that might just rewrite everything we thought we knew about space, time, and reality itself. The invisible monster. Before we can get the glitch, we have to understand the monster that hosts it. And to do that, we have to start with something we all feel every second of our lives: gravity. For centuries, we thought of gravity as a simple force, like an invisible rope pulling things toward each other. Isaac Newton gave us the math for it, and his equations work beautifully for everything from a falling apple to the orbit of the moon. But in the early 20th century, a patent clerk named Albert Einstein came along with a totally revolutionary idea. He said that gravity isn't a force at all. It's a side effect of the shape of the universe. Imagine the fabric of our universe as a big, flat, stretchy rubber sheet. This sheet isn't just space. It's space and time woven together, what we call spacetime. Now, put a bowling ball in the middle of it. The sheet curves and dips around the mass of the ball. If you roll a little marble nearby, it doesn't fall toward the bowling ball because of some mysterious pull. It's just following the curve in the sheet. It's rolling in a straight line through a curved space. That, Einstein said, is gravity. Matter tells space-time how to curve, and that curve tells matter how to move. This elegant idea, general relativity, has been proven right again and again. It perfectly predicts the orbits of planets, how starlight bends around massive objects, and even ripples in space-time called gravitational waves. But what happens when you take this idea to its absolute limit? What happens when you put something so massive, so dense on that rubber sheet that it doesn't just make a gentle curve, but a puncture? A bottomless pit? You get a black hole. And these are not just cosmic vacuum cleaners. They're the terrifying final act for the biggest stars in the universe. Picture a star hundreds of times more massive than our Sun. For millions of years, it's in a delicate balance. The nuclear furnace in its core pushes outward, fighting against the crushing inward pull of its own gravity. But eventually, the fuel runs out. The furnace goes cold. And in that instant, gravity wins. In a split second, the star's core collapses in on itself with unbelievable violence. The outer layers are blasted away in a supernova, one of the brightest shows in the cosmos. But the core just keeps collapsing. And collapsing. It squeezes itself into a space smaller than a city, then a mountain, then a pinhead. According to Einstein's theory, this collapse never stops. It goes on until all of that mass is crushed into a region with zero volume and infinite density. The gravity gets so intense that it wraps spacetime completely around itself, tearing a hole in the fabric of reality. An invisible monster is born, a spot in the universe where nothing, not even light, can ever get out. This is the stage for our story. Because while the outside of a black hole is bizarre enough, the real mystery, the glitch we're hunting, lies deep inside its silent, dark heart. The rules of the game. General relativity. To really get why a glitch is such a big deal, you have to understand the system that's supposedly crashing. For the universe at its grandest scales, stars, galaxies, the whole cosmic dance of gravity, that system is run by one of the most successful theories ever: Einstein's general theory of relativity. Think of physical laws less like unbreakable commandments and more like instruction manuals for specific tools. A hammer's manual is great for nails. But if you try to use that hammer on a screw, the tool doesn't break. You've just pushed it past what it was designed to do. General relativity is our manual for gravity. And it's an amazing one. For over a century, it's been our master key to the cosmos. When 19th century astronomers noticed Mercury's orbit was slightly off from what Newton's laws predicted, they were stumped. Some even made up a hidden planet, Vulcan, to explain it. But then came Einstein. His theory of curved space-time explained Mercury's weird wobble perfectly. The sun's huge gravity warps space-time, and Mercury is just rolling along that curve. The manual worked. In 1919, Arthur Eddington led an expedition to watch a solar eclipse. The mission? To see if light from distant stars would bend as it passed the sun, just like Einstein's theory said it would. And it did. The stars' positions appeared shifted, exactly as the math had predicted. Another win. The manual seemed flawless. More recently, in 2015, the LIGO experiment detected something Einstein predicted a century ago but figured we'd never see: gravitational waves. Two massive black holes, a billion light-years away, spiraled into each other, sending ripples through space-time. Those ripples shot across the universe, and when they finally hit Earth, they stretched and squeezed our detectors by a distance thousands of times smaller than an atom's nucleus. And yet, we saw them. The manual didn't just describe the everyday. It predicted things we hadn't even found yet. From GPS satellites that have to adjust for time moving a tiny bit faster in orbit, to the beautiful, distorted arcs of light from faraway galaxies. Lensed by the gravity of other galaxies, general relativity has aced every single test we've thrown at it. It's the most precise and elegant description of gravity we have. It's the rulebook for the cosmos. It tells us how stars are born, how galaxies form, how the whole universe evolves. And that's exactly why the glitch is so terrifying and so important. Because this seemingly perfect instruction manual has a single page where the text just turns to gibberish. A single point where the equations spit out results that aren't just strange, but physically impossible: infinities. And that page is titled Singularity. Crossing the line, the event horizon. So, our star has collapsed. Gravity won. Space-time is warped into a bottomless pit. But where does the black hole actually begin? Where's the point of no return? This line in the sand isn't a physical wall you could touch. It's a purely geometric boundary in space, defined by one scary rule. It's called the event horizon. To get it, let's use the classic river model analogy. Picture space-time not as a flat sheet, but as a river flowing toward a giant waterfall. The waterfall is the singularity at the black hole's center. Far away, the river flows slowly. You, in a boat with a powerful engine, can zip around wherever you want. That's like normal space. But as you get closer to the waterfall, the current gets stronger. You have to burn more fuel just to stay put. Trying to move away from the waterfall is a real struggle. You're fighting the flow of space itself. Now, imagine a point in the river where the water is flowing so fast that its speed is exactly the top speed of your boat. Even with your engine on full blast, pointed away from the falls, the best you can do is stand still, fighting a losing battle. That line is the event horizon. For a black hole, the current is space-time flowing inward, and the top speed of your boat is the speed of light, the ultimate speed limit in the cosmos. The event horizon is the exact spot where gravity becomes so strong that the escape velocity is faster than light. And since nothing can go faster than light, anything that crosses that line is trapped for good. It's a one-way door in the universe. From the outside, you can never even see anything cross it. Imagine watching your friend, brave or maybe just foolish, travel toward a black hole. As they get closer, you'd see some really weird stuff. First, the intense gravity would stretch them like spaghetti, a process with the lovely nickname, spaghettification. But the stranger effect is on time. According to relativity, strong gravity slows down time. From your safe spot far away, you'd see your friend's clock tick slower and slower as they neared the event horizon. Their movements would get sluggish, as if they were moving through molasses. As they reached the very edge, time for them from your perspective would grind to a dead stop. You'd see their image frozen at that boundary, getting redder and dimmer as their light loses energy fighting gravity's pull until they just fade away. You would never, ever see them cross. But for your friend, their experience is totally different. Inside their own bubble, their watch ticks normally. They'd feel the stretching, for sure, but as they approach a really big black hole, they might not even notice the exact moment they cross the horizon. There's no wall, no sign, no cosmic beep. One moment they could, in theory, turn back. The next, they can't. The river of space-time is now flowing faster than light, and every possible direction they could move now points to only one place. Down the waterfall. Toward the center. Toward the glitch. The system crash. The singularity. Okay, our traveler has passed the point of no return. The universe they knew is gone, replaced by a bizarre and hostile reality. Outside the black hole, you have freedom to move in space, but you're always dragged forward in time. Inside the event horizon, that relationship flips. Space and time swap roles. You can no longer move freely in space. The direction toward the center now acts like the future. It's not a place you go to. It's an event you will arrive at, as inevitably as you'll arrive at next Tuesday. All possible paths now converge on one final destination. That destination is the singularity. According to the equations of general relativity, our trusted manual, the singularity is a point of physical impossibility. It's what you get when all the mass of the star, and everything else that's fallen in, gets crushed into a region with zero volume. Not just small, but zero. That implies a density that is literally infinite. The curvature of space-time also becomes infinite. At this point, our perfect instruction manual simply breaks. The equations spit out infinities, which in physics is the math equivalent of a fatal error message. It's like asking your calculator to divide by zero. The system crashes. The math stops making sense, and so does our ability to describe reality. For decades, physicists wrestled with this. Could the universe really have points of infinite density where the laws of nature are just deleted? For a while, the hope was that this was just a math quirk from assuming a perfectly round, non-spinning star. Surely in the real, messy universe, things wouldn't collapse so perfectly. But in the 1960s, Roger Penrose proved that wasn't the case. He showed that as long as general relativity is correct, a singularity is inevitable once an event horizon forms. It doesn't matter if the star is spinning or lumpy. A singularity is guaranteed to be in its future. This was a deeply troubling conclusion. It meant Einstein's own theory predicted its own downfall. And this is where we start seeing it not as a failure, but as a clue. The prevailing view among physicists is that a true, physical singularity with infinite density probably doesn't actually exist in nature. Infinities in a theory are almost always a giant red flag, a sign that the theory is being pushed into a place where it's no longer the right tool for the job. The hammer is being used on a screw. General relativity is the theory of the very big and massive. It describes gravity and the smooth fabric of space-time. But the singularity is a place of immense mass that is also infinitely small. And the world of the very small is governed by a completely different instruction manual, with a whole different set of rules. The system crash of general relativity isn't an admission of defeat. It's a screaming signal that another force of nature has to step in. The glitch is a signpost pointing straight to the other great pillar of modern physics: quantum mechanics. A tale of two manuals. To understand the crisis at the heart of a black hole, you have to see the bigger picture of 20th century physics. The story was dominated by two massive, game-changing theories, two separate instruction manuals for the universe that were both spectacularly successful, yet totally incompatible. We've met the first, Einstein's general relativity, the manual for the big world of planets and galaxies, built on a smooth, predictable, geometric spacetime. The second manual describes a universe that's anything but. This is the manual for the tiny world, the realm of atoms and the particles inside them. This is quantum mechanics. And it paints a picture of reality that's fuzzy, chaotic, and ruled by probability, not certainty. In the quantum world, things don't have definite properties until you look at them. An electron doesn't have one position. It exists in a probability cloud, a smear of potential locations. You can't know both exactly where a particle is and exactly where it's going. That's the famous Heisenberg uncertainty principle. Particles can be in multiple places at once. They can be mysteriously linked across vast distances in what Einstein called spooky action at a distance, now known as quantum entanglement. This theory is, without a doubt, the most successful scientific theory ever. It's the foundation for almost all modern technology. The laser in your Blu-ray player, the transistors in your computer, nuclear power, it's all built on quantum mechanics. It's been tested to an absurd degree of accuracy. Just like general relativity, its instruction manual is perfect for its own domain. For most of the universe, this isn't a problem. The two manuals mostly stay in their own corners. General relativity handles the big, heavy stuff where quantum effects are too tiny to matter. Quantum mechanics handles the tiny, lightweight stuff where gravity is so weak it's irrelevant. A scientist studying colliding galaxies doesn't need to worry about quantum weirdness, and a particle physicist smashing protons doesn't need to worry about the curvature of spacetime. But there are two places in the universe where this peaceful separation ends. Two places where the domains of the two manuals violently collide. One was at the very beginning of the universe, in the hot, dense soup of the Big Bang. The other is at the heart of a black hole. The singularity is a place that demands both sets of rules. It's a place of immense mass, so you need general relativity. But it's also compressed into an impossibly small space, so you need quantum mechanics. And when you try to use both manuals at the same time, you get a train wreck. General relativity's smooth spacetime shatters against quantum fuzziness. Quantum mechanics' world of probabilities can't function in the infinitely warped geometry of relativity. Our two greatest theories of reality give completely contradictory answers. The math produces gibberish. This is the central crisis of modern theoretical physics. The glitch is a clue. For a long time, this conflict was seen as a massive roadblock. But a change in perspective shows it for what it really is: our biggest opportunity. The black hole singularity isn't a mistake in the universe, it's a message from the universe. That mathematical crash is the most important clue we have. It's telling us, loud and clear, you're missing something. Your theories are incomplete. There's a deeper layer you haven't seen yet. Let's go back to our instruction manuals. We have a manual for a hammer, general relativity, and one for a screwdriver, quantum mechanics. They work perfectly on nails and screws. The singularity is like some new kind of fastener that's both as big as a bolt and as fine as a screw. The hammer fails. The screwdriver fails. The problem isn't the tools. It's that you need a new, third tool you haven't invented yet. The existence of this impossible fastener is the clue that such a tool must exist. The singularity is that impossible fastener. It's the one place where nature forces our two best theories into the same room and makes them talk. And their failure to get along tells us they must both be just approximations of a more fundamental, underlying theory, a theory that can handle both the very large and the very small in one elegant package. Physicists call this hypothetical theory quantum gravity. The search for a theory of quantum gravity is often called the Holy Grail of modern physics. It's the quest to read the deepest source code of the universe. The singularity, then, is transformed. It's no longer a point of failure. It is our only real window into the world of quantum gravity. It is a natural laboratory where energies and densities are pushed to levels we could never dream of creating on Earth. By studying the glitch, by trying to figure out how a better theory would fix the impossible infinities, we are trying to reverse engineer the laws of this deeper theory. So what would a theory of quantum gravity do? It would get rid of the singularity. It would probably tell us that space-time isn't smooth and continuous at the tiniest possible scales. It might be pixelated, made of tiny, indivisible atoms of space and time. If that's true, a collapsing star couldn't shrink to an infinitely small point. It would be stopped by the fundamental graininess of spacetime itself. There would be a minimum possible size and a maximum possible density. The infinities would disappear. The glitch would be fixed. The singularity, therefore, isn't the end of physics. It's the beginning of new physics. It's a message in a bottle, washed up from an unknown continent, telling us there is more to explore. It's the glitch that reveals a more sophisticated operating system running underneath the reality we see. The source code of reality, quantum gravity. So, the glitch points to a deeper theory of quantum gravity. But what would that theory actually look like? What happens to the singularity when you apply these hypothetical new physics? This is the absolute frontier of science, and there's no single answer. Instead, there are a few exciting, competing ideas. One of the most famous is string theory. It has a beautifully simple core idea. If you could zoom in on any particle, an electron, a photon, you wouldn't see a point. You'd see a tiny, vibrating, one-dimensional loop of energy, a string. Different particles are just different notes played on this cosmic string. One note might be an electron, another a photon. The laws of physics become the rules of harmony. In this picture, because strings have a tiny but finite size, they can't be squeezed into zero volume. This neatly avoids the singularity. Some versions of string theory suggest a black hole's center might be a fuzzball, a messy, tangled ball of all the strings that ever fell in. From the outside, it looks just like a regular black hole, but inside, information isn't destroyed, it's just stored in the fuzzball. The glitch is gone, replaced by a ball of vibrating energy. Another leading contender is loop quantum gravity, LQG. This theory takes a different route. It suggests that spacetime itself is woven from a network of finite, indivisible loops, atoms, of spacetime. You can't have a space smaller than one of these loops. From this viewpoint, a collapsing star can't crush down forever. When it hits the fundamental size of these spacetime loops, it runs into a powerful repulsive force from the quantum structure of space itself. This quantum pressure stops the collapse. What forms isn't a singularity, but an incredibly dense object called a Planck star. The matter would then bounce. Because of extreme time dilation, this bounce would take billions of years from an outside perspective. We don't know which of these ideas, if any, is right. They are all deeply mathematical and incredibly hard to test. But they all share a core idea. The singularity isn't a real thing. It's a placeholder for a new, richer, and far stranger quantum reality. The system crash is a gateway to a world of fuzzballs, Planck stars, and a pixelated spacetime. The glitch is the portal. The other glitch, the Big Bang. The singularity at the heart of a black hole is a profound mystery. But what makes this story even more compelling is that it's not the only place our physics breaks down. There's another, equally famous glitch in our understanding of the universe. It's not a place in space, but a moment in time. The very beginning. According to general relativity, if you run the clock backward on our expanding universe, everything gets closer and closer together. The density and temperature skyrocket. Just like a collapsing star, if you rewind far enough, you reach a point where the entire observable universe was crushed into a region of zero volume with infinite density and temperature. You reach another singularity. This is the Big Bang. And just like the black hole singularity, this one is almost certainly not a real physical state. It is another division by zero error message from general relativity. It's another sign that Einstein's theory, for all its power, can't be the final word. The conditions at the Big Bang, unimaginable energy in a subatomic space, are, once again, the perfect storm where general relativity and quantum mechanics must both apply. And once again, they fail. This is a stunning realization. The two greatest mysteries in science, what's inside a black hole and what happened at the beginning of time, are, at their core, the same problem. They are both singularity problems. They both show the limits of our knowledge and point to the same missing piece: a theory of quantum gravity. This connection completely transforms the quest. We're not just solving an astronomical puzzle. We're trying to solve the riddle of our own origin. A theory of quantum gravity wouldn't just tell us what happens inside a black hole. It would lift the veil on the first moments of creation. It might describe a universe before the Big Bang. Some models, like those from loop quantum gravity, suggest a big bounce, where a previous universe collapsed and re-expanded into ours. The glitches are connected. The physics that smooths out the singularity inside a black hole is the same physics that will describe the birth of the cosmos. The source code that fixes the crash at the end of a star's life is the same code that wrote the first line for our universe. By studying these invisible monsters, we are, in a very real sense, studying creation itself. We started this journey with a problem, a glitch, where our best theories of physics crash and burn. We looked past the point of no return and into the warped heart of a black hole, searching for that impossible point of infinite density. But what we found wasn't an error. It was a signpost. The singularity isn't a breakdown of the universe. It's a breakdown of our description of it. It's where a simpler law reveals its limits and points to a deeper one. Newton's laws weren't wrong. They were just an approximation of Einstein's relativity. And it looks like Einstein's relativity is an approximation of a still deeper theory of quantum gravity. The laws of physics don't break. They transform, revealing more of the universe's underlying code. The glitch inside every black hole connects the largest objects in the cosmos with the smallest possible scales. It links the death of a star with the birth of the entire universe. This isn't a failure to be upset about. It's a puzzle to be solved. And in solving it, we are writing the next chapter in our understanding of reality. The glitch isn't a bug. It's a feature. It's a tantalizing peek at the universe's true operating system. And the greatest mystery of all is the one physicists are trying to answer right now. What else is written in that code? If you find these cosmic mysteries as fascinating as we do, consider subscribing and joining our journey to the edges of what we know. The universe is full of glitches, and every one is a door to a new discovery. Let us know in the comments. What do you think is really at the heart of a black hole? A fuzzball, a Planck star, or something we haven't even imagined yet? The unbreakable barrier at the edge of space-time. The universe has rules. Billions of them. They're written in the language of math, and they govern everything from the whisper light dance of a photon to the cataclysmic crash of galaxies. We call them the laws of physics. For most of our history, we've learned these laws from the safety of our own calm, predictable corner of the cosmos. Here, things at rest stay at rest, every action has an equal and opposite reaction, and time marches forward at a nice, steady pace. But what happens when you leave that safety? What happens when you journey to the ragged edge of reality itself? To places where the familiar rules seem to warp, bend, and even break. Places where time can slow to a crawl and space can stretch into infinity. Out there, in the most extreme environments the cosmos has to offer, it feels like anything is possible. That every law can be broken. But that's not quite true. There is one law, one fundamental principle so vital to the fabric of reality that the universe will build infinite walls and erect impossible barriers just to protect it. A rule that, as far as we know, can never, ever be broken. What if I told you that at the very edge of reality, where time itself can stop and space can stretch into infinity, there is one rule that the universe protects at all costs? We're going on a journey to the most extreme places we know of, to find the one unbreakable law of physics. We'll race toward the speed of light, and we'll fall to the edge of a black hole. We will see the universe's most sacred rules appear to crumble before our very eyes. And in the wreckage, we'll find the one thing the cosmos refuses to give up. The illusion of broken laws. When we say a law of physics is broken, what do we really mean? It's a dramatic phrase, right? Sounds like cosmic anarchy. But the truth is a lot more subtle and way more elegant. Think of the laws we know not as rigid commands, but as incredibly accurate descriptions of reality. Within a certain context. For centuries, our context was the world according to Sir Isaac Newton. His laws of motion are masterpieces. They let us predict the arc of a cannonball, build bridges that defy gravity, and send probes to other planets. For a long, long time, they seemed unbreakable. And then, we started to push the boundaries. We built machines that could fling particles at unbelievable speeds. We saw stars so massive their own gravity crushed them. And in these new, extreme contexts, Newton's elegant laws started to show cracks. They didn't break, they just became incomplete. They were a brilliant approximation of a much deeper, much stranger reality. When you hear that the laws of physics break down, it's really just a dramatic way of saying that our current maps don't cover that territory. This is how science works. A law isn't a command nature has to obey. It's a model we've built. And when we venture into new territory, sometimes we need a new model. Enter Albert Einstein. In 1905, his theory of special relativity changed everything. He started with two simple, but revolutionary, ideas. First, the laws of physics are the same for everyone who's not accelerating, and second, the speed of light in a vacuum is the same for everyone, no matter how fast they're moving. From those two ideas, a new universe emerged. One where space and time weren't separate things, but were woven together into a single fabric, space-time. And the old rules didn't quite fit anymore. Einstein's theories didn't throw Newton out. They expanded on him. At the slow, everyday speeds we live at, Einstein's equations give you pretty much the exact same answers as Newton's. But as you get closer to the cosmic speed limit, the speed of light, Newton's world gracefully fades out, and Einstein's far stranger reality takes over. The laws don't shatter, they transition. The universe is built on limits like these. Often, when a theory seems to break, it's because its equations are getting close to a limit and spitting out impossible answers, like dividing by zero or landing on infinity. These infinities aren't failures of the universe. They're warnings from the math. They're signposts that read, your current map ends here. Beyond this point, new rules apply. And the two most profound limits we've ever found are at the very edge of space-time. The speed of light and the abyss of a black hole. To find our unbreakable law, we have to go to these barriers first and see what happens when we try to cross them. The first barrier. Approaching light speed. Imagine you're in the most advanced spaceship ever built. Your destination isn't a place, but a speed. 299,792 kilometers per second. The speed of light, c. It's not just a number. It's the ultimate speed limit, the fastest anything can travel through space-time. You fire up the engines. The acceleration pushes you back into your seat. Through the cockpit window, the stars begin to streak. At 10% of light speed, it's exhilarating. At 50%, the universe starts to look weird. Starlight from up ahead looks blue shifted, its wavelengths compressed and more energetic. Light from behind you is redshifted, stretched into the redder end of the spectrum. Now you push the engines harder, accelerating to 90% of the speed of light. And this is where reality really starts to warp. The first thing you'd notice is that, for you, everything feels perfectly normal. Your heart beats steadily, your watch ticks once per second. Inside your ship, the laws of physics haven't changed a bit. But for someone watching you from Earth, it's a completely different story. Through a powerful telescope, they'd see your ship's clock ticking much, much slower than their own. They'd see you moving in slow motion. This is time dilation. Time itself is running slower for you, relative to them. At the same time, from their perspective, your 100-meter-long spaceship appears squashed in its direction of motion. It might look like it's only 50 meters long now, or even 20. That's length contraction. To the outside world, you are both slowing down in time and shrinking in space. But you're determined to reach C. You push the engines to their absolute maximum. You go from 90% of light speed to 99%. From 99% to 99, 9%. From 9% to 99,999%. But you never quite get there. Why? Because the universe itself is fighting back. As you get faster, something strange happens with energy. The amount of energy required to increase your speed isn't constant. The closer you get to the speed of light, the more energy it takes to go just a little bit faster. It's a game of cosmic diminishing returns. The energy you pour in is contributing more to your momentum than to your actual velocity. To go from 99% to 99.9% light speed takes a huge amount of energy. But to get from there to 99% takes even more. As your velocity gets closer and closer to *C*, the energy needed to accelerate further approaches infinity. This is the unbreakable wall. To reach the speed of light, you would need an infinite amount of energy. You'd need more energy than exists in the entire universe just to make that final leap. And this isn't just a theory. At particle accelerators like CERN, scientists have pushed protons to 999,999% of the speed of light. They have seen firsthand the monumental energy required to get there. They have pushed right up against this infinite barrier. So, the first great boundary holds. You can get incredibly close to the speed of light, but if you have mass, you can never reach it. The universe forbids it by demanding an infinite price. But this is just our first stop. To find our unbreakable law, we now have to travel to a place where space and time collapse entirely. The edge of a black hole. The second barrier. The edge of a black hole. Black holes are the universe's ultimate monsters. They're what's left when a colossal star dies and its own gravity crushes it down into an impossibly small space. They are regions of space-time so violently curved that they rip a hole in the fabric of reality itself. The boundary of this region, the point of no return, is called the event horizon. It's not a physical surface you could touch or bump into. It's a threshold. Cross it, and you're lost to our universe forever. Let's watch what happens. Imagine you're in a probe, hovering a safe distance away. You release a smaller, secondary probe, watching it drift toward the event horizon. From your safe vantage point, you witness one of the strangest things in all of physics. As the probe gets closer to the horizon, it appears to slow down. The black hole's immense gravity is warping time, making time near the horizon run slower relative to you. The probe seems to take minutes, then hours, then years to cover the last few meters. The light from it gets stretched out, becoming redder and dimmer. Eventually, it looks like it freezes completely, its image smeared across the horizon, fading over an infinite amount of time. From where you're watching, it never actually crosses. But for the probe itself, the story is tragically different. It doesn't feel itself slowing down or freezing. From its own perspective, it just sails smoothly across the event horizon. No drama, no signpost, no wall. Just a silent, invisible boundary crossed. Inside, the rules change completely. The roles of space and time actually switch. Out here, we can move anywhere we want in space, but we're forced to move forward in time. Inside a black hole, you're now forced to move in one direction in space, inward, toward the center. The future is no longer a when, it's a where, the singularity. And you can't stop yourself from getting there any more than you can stop yourself from getting to next Tuesday. As you fall, another horrifying effect takes over. Spaghettification. The gravitational pull on the part of you closer to the center is way stronger than the pull on the part farther away. This difference in force starts to stretch you, pulling you into a long, thin strand of atoms. It's a process so powerful that nothing can resist it. And at the very heart of it all is the final mystery, the singularity. According to Einstein's theories, this is a point of zero volume and infinite density, where all the black hole's mass is crushed together. Space-time curvature becomes infinite, and our laws of physics just stop. They produce only infinities, that mathematical signpost telling us, again, that our map has run out. Now, physicists don't really think a point of actual infinite density exists. They believe the singularity is where general relativity, the law of the very large, finally crashes into quantum mechanics, the law of the very small. To understand it, we'd need a new theory, a quantum theory of gravity, which we don't have yet. The singularity is the ultimate boundary, not just of space and time, but of our own understanding. So, we've journeyed to two of the most extreme boundaries in the cosmos. We've been blocked by an infinite energy cost at the speed of light, and we've stared into the infinite density of a singularity. At both edges, the universe throws up a wall of infinities. And this raises the biggest question of all. Why? What is the universe so desperately trying to protect? We are right on the verge of uncovering the single most fundamental rule of our universe. Look, I know this is heady stuff, but it connects us to the grand story of the cosmos. If you love grappling with these big questions and want to keep exploring the frontiers of science, hit that subscribe button. Your support is what lets us make these journeys. Now, let's get back to the edge of space-time and find the answer we came for. The Great Unraveling. Why do we need a barrier? So, we've seen the barriers. The speed of light is a wall of infinite energy. A black hole is a one-way trip to a place where our physics breaks. These aren't just random rules. They are core features of our universe's operating system. And to understand why they exist, we have to stop thinking about speed and gravity and start thinking about something much more fundamental: information. The speed of light, C*, isn't just the speed of photons. It's the speed of information. It's the maximum speed at which any cause can travel through the universe to create an effect. When you flip a light switch, the room can't light up faster than the light itself travels from the bulb to the walls. If the sun were to suddenly vanish, Earth would keep orbiting for 8 minutes, because that's how long it takes for the asterisk information of the sun's absence carried by gravitational waves, which also travel at c*, to reach us. This speed limit creates a structure for spacetime. For any event, let's say, a star exploding, we can divide the entire universe into 3 zones. There's the past, which contains all the events that could have possibly caused the explosion. There's the future, which contains all the events that the explosion could possibly affect. And then there's a vast region of spacetime outside those 2 zones, called elsewhere. Events elsewhere can't affect the explosion, and the explosion can't affect them, because there just isn't enough time for a signal to travel between them, even at light speed. This structure protects a principle that's so deep, we barely even think about it. An effect cannot happen before its cause. This is the principle of causality. It sounds simple, obvious, even. Of course, a glass can't shatter before it hits the floor. The entire story of our lives, and of the universe itself, is built on this logical, forward march of cause and effect. One thing leads to another. But what if you could break that rule? What if you could send a signal faster than light? The results wouldn't just be strange, they'd be paradoxical. They would unravel the logical fabric of reality. And that is what the barriers at the edge of spacetime are built to prevent. The climax, the unbreakable law revealed. Here it is. The one law we've been looking for. The unbreakable barrier at the edge of spacetime isn't a speed or a place. It's a principle. Causality. ***. The universe will bend space, stop time, and demand infinite energy for one simple reason. To make sure that cause always comes before effect. The speed of light isn't just a speed limit, it's the ultimate enforcer of causality. To see why, let's do one last thought experiment. Let's break the rules. Imagine we built a tachyonic telephone, a device that can send a message faster than light, let's say, instantly. We have 2 operators. Alice, on a spaceship moving away from Earth at 80% light speed, and Bob, who stays home. At noon, Bob's time, he spots an asteroid that's going to hit Earth in 1 hour. In a panic, he uses the tachyonic telephone to send an instant warning to Alice. Now, because of special relativity, things get weird for Alice. She's moving so fast that her now isn't the same as Bob's now. An event Bob sees at noon, Alice might see at 11:55 a.m. her time. So when she gets Bob's instant message, it arrives at 11:55 a.m. From her point of view, she now knows about the asteroid 5 minutes before Bob even sent the message. This lets her do something truly impossible. She uses her own tachyonic telephone to send a message back to Bob that says, "Don't worry, I got your message about the asteroid." Bob receives this reply at 11:58 a.m. on his clock. He's staring at a reply to a warning he won't send for another 2 minutes. He has received an effect before its cause. The timeline is broken. This isn't just a weird brain teaser. It's a universe-breaking paradox. If Bob gets the warning at 11:58 a.m., he could just not send the message at noon. But if he never sends the message, then Alice could never have replied to it. The entire sequence of events logically eats itself. It becomes a story that makes no sense. This is what faster than light travel or communication would allow. It would let you send information into your own past. It would create time loops where an event can be its own cause, making a mockery of logic. The universe would cease to make sense. The infinite energy requirement to reach light speed is the universe's firewall against this paradox. The event horizon of a black hole, trapping all information inside, is another. They are both physical manifestations of the same logical rule. Other laws might seem fundamental, like the conservation of energy, but even they get weird at the quantum level. But causality is different. It's the logical bedrock. Without it, there's no before and after, no if and then. Physics, as we understand it, becomes impossible. The unbreakable barrier is the speed of causality, which just so happens to be the speed of light. It's not a limitation, it's a protection. It's the one rule the universe cannot afford to break. When we started this journey, we were looking for an unbreakable rule at the violent, twisted edges of space-time. We raced toward the cosmic speed limit, where time slows and the energy cost becomes infinite. We fell to the point of no return at a black hole, where space and time swap roles and point only toward oblivion. In these places, the familiar laws of our world bent in ways that seem impossible. Time, space, energy, all the things we thought were fixed revealed themselves to be fluid and strange. Yet, beneath it all, we found the one principle these cosmic barriers are built to protect. The unbreakable law isn't physical, it's logical. Cause must come before effect. The universe we live in isn't just a random collection of particles and forces. It's a story. A sequence of events unfolding through time, each one leading to the next. The unbreakable barrier of causality is what ensures that this story can be told, that the pages are turned in the right order. It ensures that the universe itself makes sense. So while we might dream of faster-than-light travel, we have to face the profound reality that the very structure of the cosmos is designed to prevent it. The universe, it seems, would rather bend itself into infinite shapes than allow a single paradox to ruin its own story. Which leaves us with one final, nagging question. If causality is the one law the universe will bend its own rules to protect, what does that tell us about the nature of time itself? Is it just another dimension, or is it something more? A story that has to be told in the right order. The equation that proves the universe is a lie. We're all taught that math is the language of the universe. It's the one tool we've got that seems to describe reality with this perfect, almost divine precision. From the arc of a thrown ball to the majestic dance of galaxies, equations map out the cosmos and our place in it. They feel like the bedrock of our understanding the source code of existence itself. But what if I told you that in the most extreme, most violent places in the cosmos, our most trusted equations don't just get a little fuzzy? What if I told you they scream that the universe shouldn't exist at all? They spit out impossible, nonsensical answers, infinities that suggest reality itself should just shatter. And yet, here we are. The universe is chugging along just fine, governed by an order our own mathematics tells us is impossible. This is the story of that impossibility. It's a detective story. The crime scene is the heart of a black hole. The witnesses are our two most fundamental theories of reality. And the culprit is something we never saw coming. This is the story of why our broken equations don't mean the universe is broken, but that our whole understanding of truth has been wrong all along. The perfect crime scene. A point of infinite lies. To get to the bottom of this cosmic mystery, our investigation has to start at the most extreme object we know of. A black hole. On the outside, a black hole is almost insultingly simple. It's a chunk of space-time where gravity is so intense that nothing, not even light, can get out. The edge of this zone is called the event horizon. Think of it like a river that turns into a waterfall, and the water starts flowing faster than you could ever hope to swim. Once you drift past a certain point, there's no going back. The event horizon is that point of no return for space and time itself. Cross it, and you're lost to the outside universe forever. Our ability to even describe this beast comes from one of the pillars of modern physics. Albert Einstein's theory of general relativity. Back in 1915, he completely reimagined gravity. Newton saw it as some mysterious force pulling things together. Einstein showed it wasn't a force at all. It's just what happens when mass and energy warp the very fabric of space-time. Imagine putting a bowling ball on a trampoline. It creates a dip. A marble rolling nearby will curve towards it, looking like it's being attracted to the bowling ball. Einstein said that space-time is the trampoline. Stars and galaxies are the bowling balls, creating curves that guide everything else. This theory has been tested to an insane degree of accuracy. It predicted that starlight would bend around the sun, explained a weird little wobble in Mercury's orbit, and even predicted gravitational waves ripples in space-time, which we've now actually detected. By every measure, general relativity is a masterpiece. But when we point its beautiful equations at the heart of a black hole, they deliver a verdict that isn't just wrong. It's impossible. The equations predict that all the stuff that falls in entire stars, planets, gets crushed into a region of zero volume and infinite density. This point is called a gravitational singularity. Let's just stop and think about what that means. Infinity isn't a number you can find in the real world. It's an idea. Having a physical object with infinite density means the curvature of space-time becomes infinite. Gravity becomes infinitely strong. And at that point, the very equations that predicted its existence completely short-circuit. They can't tell you what happens next. Space-time, as a concept, just stops. The laws of physics, as we know them, shatter. Physicist Kip Thorne called the singularity the point where all laws of physics break down. It's a mathematical error message written into the source code of the universe. When your calculator flashes error, it doesn't mean reality just crashed. It means you asked it to do something nonsensical, like divide by zero. A singularity is physics' ultimate error message. It tells us that general relativity, as powerful as it is, has been pushed too far. This is our crime scene. At the center of these cosmic monsters, our best theory of the big-scale world tells us that reality should end. But the universe doesn't seem to care about our math. It keeps on going. This isn't a small rounding error. It's a fundamental contradiction. And to understand why, we need to bring in our first suspect. The first suspect. The comfortable failure of Isaac Newton. Before Einstein, there was Isaac Newton. For over 200 years, his laws of motion and gravity were the undisputed champs. Laid out in his Principia Mathematica back in 1687, these laws were a total triumph. They described the world with stunning precision. Newton's second law, force equals mass times acceleration, F equals ma, might be the most famous equation in all of physics. It's what lets engineers build bridges that last for centuries and helps NASA slingshot a probe to Mars. It just works. It's intuitive. For everything in our daily lives, from a falling apple to the orbit of the moon, Newton's laws are basically true. And yet, we know they're fundamentally wrong. Or, to be more accurate, they're incomplete. Newton's tidy universe was built on a few assumptions that seemed totally reasonable at the time. He figured space was a fixed, unchanging backdrop, and time was a universal clock, ticking away at the same rate for everyone. But the universe is a lot weirder than the world Newton could see. His laws start to fall apart at two extremes: the very fast and the very small. First, the very fast. According to Newton, if you keep pushing something, it'll keep accelerating, faster and faster, with no limit. But Einstein's theory of special relativity showed us there is a cosmic speed limit, the speed of light. As you get closer to it, it takes more and more energy to speed you up. F equals ma is no longer so simple. At everyday speeds, you'd never notice this. But for a particle whizzing around an accelerator, it's reality. Newton's laws fail. Second, the very small. Zoom down to the world of atoms, and the neat, clockwork universe of Newton dissolves into a fuzzy, probabilistic fog ruled by quantum mechanics. An electron doesn't just orbit a nucleus like a planet. It exists in a probability cloud, a region where it's asterisk likely to be. You can't know its exact position and its exact momentum at the same time. This isn't a problem with our tools. It's a fundamental rule of the game, called Heisenberg's uncertainty principle. So, was Newton a failure? Were his laws a lie? Not at all. And this is the first major clue in our investigation. Newton's laws weren't wrong. They just had a limited domain of validity, a set of conditions where they're a good enough description of reality. Think of it like a recipe. A recipe for a chocolate cake is a brilliant bit of chemistry that reliably makes a delicious cake. But if you try to use that same recipe to bake a loaf of bread, you're going to have a bad time. Does that make the cake recipe a lie? Of course not. It just means you used it for the wrong job. Newton's laws are a recipe for the world of medium-sized things at medium speeds. And in that domain, they are still used every single day. They are a phenomenally powerful approximation of a deeper reality. But they are not the whole reality. The failure of Newton's laws at the edges wasn't a crisis. It was progress. It showed scientists exactly where the map ended and pointed them toward a deeper theory. This brings us back to our crime scene. We see Einstein's general relativity, the very theory that replaced Newton's, now failing in the exact same way. It's producing infinities, a sign that we've stepped outside its domain of validity. The singularity isn't a real place. It's a big red warning sign on our map of physics that reads, "Here, the model no longer applies." This pattern is the scientific method in action. But to really crack this case, we need to look at our other main theory of reality, the one that governs the world where Newton's laws first broke. The world of the quantum. The accomplice. The unsettling strangeness of quantum mechanics. If general relativity is the sweeping theory of the very large planets, stars, galaxies, then quantum mechanics is its bizarre, brilliant twin. It's the theory of the very small, atoms, electrons, photons. And where general relativity is smooth and geometric, quantum mechanics is chunky, probabilistic, and fundamentally weird. Quantum mechanics is, and this is not an exaggeration, the most successful scientific theory in human history. Its predictions have been proven right to a mind-boggling degree of accuracy. The entire digital world, from the chips in your computer to the lasers in a Blu-ray player, is built on it. So this isn't some abstract, what-if idea. It's the foundation of modern tech. Yet, the reality it describes is completely alien. At the quantum scale, particles can be in many places at once in a superposition. They only pick a spot when we look. A particle's properties, like where it is and where it's going, are linked in a trade-off called the Heisenberg uncertainty principle. The more you know about one, the less you know about the other. Reality at this level is just fundamentally fuzzy. Even weirder, particles can become entangled, their fates linked no matter how far apart they are. Einstein famously called this spooky action at a distance. For decades, these two great theories, general relativity and quantum mechanics, pretty much ignored each other. One handled the big stuff, the other handled the small stuff. The problem is, our universe has places where both have to be true at the same time. And when they meet, they don't just disagree. They go to war. The singularity inside a black hole is the ultimate battleground. It's a place of enormous mass and gravity, clearly general relativity's turf. But it's also crushed down to an infinitesimal point, exactly where quantum effects should take over. To describe it, we need a theory of quantum gravity. And we don't have one. When we just try to jam them together, the math breaks down even more spectacularly than before. The problem of infinities comes back with a vengeance. For instance, quantum theory's calculation for the energy of empty space comes out with a number so huge, about 120 orders of magnitude larger than what we actually measure, that it's been called the worst theoretical prediction in the history of physics. The conflict is deep. General relativity demands that spacetime is a smooth, continuous sheet. Quantum mechanics says the world is made of discrete, grainy chunks. They're written in different languages and describe different realities. So here's our second accomplice. Quantum mechanics, for all its success, also has its limits. It's a theory of the small that doesn't include gravity. And just like Newton's laws broke down at the extremes, our two modern pillars of physics are showing us their own breaking points. The singularity is where their domains collide. The infinite density and infinite gravity are symptoms of this theoretical clash. This reveals a deeper truth. The problem isn't just one equation failing. The problem is that our entire description of reality is split in two. We have one set of laws for the big and another for the small. The universe, however, isn't split. It's one thing. It works just fine in places like singularities, where our theories throw their hands up. And that brings us to the heart of the mystery. The lie wasn't in the equations. It was in our assumption about what an equation is supposed to be. Cracking the case. The truth of broken equations. So we've arrived at the central paradox. We have two sets of laws, one for the cosmos, one for the quantum realm. Both work incredibly well on their own turf. But where their turfs overlap, like inside a black hole or at the Big Bang, our math produces gibberish. It screams infinity and tells us the universe should crash. But it doesn't. The contradiction isn't in nature, it's in our description of it. And this is where we crack the case. The fact that our equations break isn't a failure. It's the most important clue we have. Let's go back to that idea of a domain of validity. Every theory we've ever come up with makes simplifying assumptions. Newton assumed space and time were fixed. Einstein's general relativity assumes matter is smooth, ignoring its chunky quantum nature. Quantum mechanics usually assumes spacetime is flat, ignoring gravity. These aren't mistakes. They're necessary shortcuts to make the math work. They define the theory's domain. The infinities are just mathematical alarm bells telling us we've wandered outside that safe domain. An infinity in an equation doesn't mean a physical thing has become infinite. It means the theory you're using has hit a wall and can no longer give you a sensible answer. This changes everything. We've been acting like a baker who's furious that their cake recipe made a terrible loaf of bread. We've been blaming the recipe instead of realizing we were using it for the wrong thing. The universe isn't a lie. The lie was our belief that any one of our theories could be the asterisk final truth, the master recipe for everything. This is the beautiful honesty of science. A scientific theory isn't a statement of eternal truth. It's a model. It's a map. And as the saying goes, the map is not the territory. A map of your city is great for getting around, but it doesn't show you every crack in the sidewalk. And if you try to use that city map to navigate the ocean, it becomes useless pretty fast. The fact that our theories break is how we learn. The failure of classical physics gave us relativity and quantum mechanics. The current failure of those two to get along is now pointing the way to an even deeper theory, a theory of quantum gravity. Scientists aren't upset by this, they're thrilled. The breakdown is where the new physics is hiding. Think of it this way. The laws of physics don't break at their limits. They hand off to a deeper law we haven't found yet. Newton's laws hand off to relativity at high speeds. Now, we see that general relativity and quantum mechanics must themselves hand off to a new theory in the furnaces of black holes and the Big Bang. So, the equation that proves the universe is a lie. Is any equation we push into a singularity. But what it's really proving is that our assumption of its universal truth is the lie. The universe itself runs on a single, unified set of rules. It's our knowledge that's fragmented. And it's at the very edge of that knowledge, where our beautiful equations shatter, that we find the path forward. The next investigation. The hunt for a deeper truth. Realizing our best theories are just incomplete maps isn't the end of the story. It's the start of the next, grander investigation. The search for a unified theory of quantum gravity. And physicists are chasing some seriously mind-bending leads. One of the most famous is asterisk string theory. It suggests that the most basic ingredients of the universe aren't tiny little points, but unimaginably small, vibrating strings of energy. Everything we see an electron, a photon, a quark is just a different note being played by these strings. One of these notes, the theory predicts, is the graviton, the quantum particle of gravity. In this way, string theory naturally unites quantum mechanics and gravity, smearing out the pinpoint infinities and solving the singularity problem. The catch? It requires extra, hidden dimensions of space and operates at energies we can't get close to, making it incredibly hard to test. Another top contender is asterisk loop quantum gravity. While string theory changes the particles, LQG changes the spacetime they live in. It suggests that the fabric of spacetime itself isn't smooth, but is made of discrete, indivisible chunks, atoms, of space and time. In this picture, you can't have a region of zero volume, so a singularity is impossible. Instead, as a black hole collapses, it would hit a maximum density and then bounce. LQG is a beautiful idea, but like string theory, it's still waiting for an experimental test to prove it right. Then there's maybe the most radical idea of all. The asterisk holographic principle. This came from the weird fact that all the information a black hole can hold seems to be stored on its 2D surface, the event horizon, not in its 3D volume. The principle takes this and runs with it, suggesting that our entire 3D universe might just be a projection, a hologram of information stored on a distant, 2D surface at the edge of the cosmos. It's a bizarre thought, but it provides a powerful mathematical link between gravity and quantum information, potentially resolving the paradoxes where they meet. These ideas, string theory, loop quantum gravity, the holographic principle, are all works in progress. They are the prime suspects in the hunt for the next layer of reality. One might be right, they might all be wrong, or they might each be a piece of an even stranger puzzle. But what they all have in common is that they were born from the breakdown of our old theories. They take the error messages from physics not as failures, but as instructions. The infinities and paradoxes are the clues left at the crime scene, telling us where to look next. So, we come back to where we began. The equation that proves the universe is a lie. We've seen that deep inside a black hole, our best equations predict a singularity, a point where the laws of physics break. We've seen that our two great theories, general relativity and quantum mechanics, are locked in a Cold War. But the lie was never in the universe. The lie was in our assumption, the belief that our models were a perfect copy of reality, instead of what they are: powerful, but limited, maps. A map isn't the territory, and an equation isn't the universe. The breakdown of an equation isn't a sign of cosmic chaos. It's a signpost. It's the universe showing us the edge of our own understanding and daring us to look deeper. The failure of Newton's laws gave us Einstein. The failure of classical physics gave us the quantum world. And the current, beautiful, spectacular failure of our two best theories to unify is the single greatest engine of discovery in physics today. The universe doesn't have infinities. Our theories do. The universe doesn't have paradoxes. Our models do. The universe simply is, operating on rules so deep and elegant we haven't even found the right language for them yet. We are detectives in the middle of a cosmic mystery, and every time we find a flaw in our logic, we get one step closer to the truth. The equations are not a lie. They are a story. The story of our relentless, profoundly human quest to figure this all out. And the most exciting chapters are the ones we have yet to write. If you loved digging into the biggest questions in the universe, from black hole paradoxes to the mysteries of quantum reality, make sure you subscribe and join the journey. There are always more layers to pull back. Reality's ultimate glitch is saving the universe. The universe, as we know it, probably shouldn't exist. At its very foundation, reality appears to be broken. If you could zoom in past the atoms, past the nucleus, to the smallest possible scale, you wouldn't find a smooth, stable fabric of space-time. You'd find chaos. A seething, bubbling, violent mess that physicists call quantum foam. This is what our best theories predict. A fundamental glitch in the cosmic operating system. A glitch so profound, it poses a paradox. Why hasn't this microscopic chaos destabilized everything? But it doesn't. We're still here. The stars are shining, the planets are orbiting, and the laws of physics are holding steady. So, why? What if I told you that this cosmic paradox, this theoretical glitch at the heart of everything, might be the very thing holding our reality together? What if the fatal flaw is actually the ultimate feature? This is the story of how the universe's biggest conceptual mistake might just be the one thing saving it from itself. A story of how instability at the bottom can breed unbreakable stability at the top. To understand how, we first need to appreciate the beautiful, elegant, and dangerously incomplete picture of the universe we once held. The smooth, deceptive universe of Einstein. For centuries, our view of the cosmos was one of clockwork elegance. Planets moved in knowable orbits, stars burned with a steady fire, and the space between them was just empty space. A void. A background stage for the drama of the universe. It was a picture of serene order. Then, in the early 20th century, Albert Einstein completely shattered and rebuilt that stage. He gave us general relativity, and with it, a whole new vision of reality. In Einstein's universe, space isn't an empty backdrop, it is a asterisk thing. It's a dynamic, physical fabric, woven together with time into a four-dimensional entity. Space-time. And this fabric isn't rigid. It's flexible, it stretches, and most importantly, it warps. You've probably seen the classic analogy: a bowling ball on a rubber sheet. A massive object, like a star, placed on the spacetime fabric creates a depression, a curve. Other objects, like comets, don't feel a mysterious pull of gravity. They're simply following the curves in the fabric created by that larger mass. This was a revolution. Gravity wasn't a force reaching across the void, it was the asterisk geometry of spacetime itself. And this picture worked beautifully. It predicted the bending of starlight around the sun, which was confirmed during the 1919 solar eclipse. It explained tiny, nagging anomalies in Mercury's orbit that Newtonian physics just couldn't account for. It gave us the math to understand the expansion of the universe, the lives of stars, and the existence of objects so dense they would punch a hole in spacetime. Black holes. The universe of general relativity is majestic. It's a universe of sweeping curves and cosmic symphonies on a grand, smooth canvas. Everything is continuous and predictable. If you know the state of the universe now, you can, in principle, calculate its entire future and past. From a plane flying high above the ocean, the surface of the water looks perfectly smooth, a vast, unbroken sheet of blue. That's Einstein's spacetime. A continuous, unbroken, and fundamentally stable reality. For a long time, this was our most profound understanding of the universe. It was a reality you could trust. But even as Einstein was building his grand cathedral of spacetime, another revolution was brewing in the world of the very small. A revolution that was about to reveal that, up close, that smooth ocean was a violent, chaotic storm. This other revolution, quantum mechanics, didn't just disagree with Einstein's smooth picture. It suggested such a picture was impossible. And in the clash between these two titans of physics, our understanding of reality would be torn apart, revealing a perplexing glitch at its very core. The quantum wrench in the cosmic machine. While Einstein was looking at the stars and imagining a gracefully curved spacetime, other physicists were looking in the opposite direction. They peered into the heart of the atom, into a realm so small and bizarre that our everyday rules simply stop applying. This was the world of quantum mechanics, and it wasn't a world of smooth curves. It was a world of jumps, probabilities, and a deep, unshakable uncertainty. One of its cornerstones is Werner Heisenberg's uncertainty principle. In its famous form, it says you can't know both the exact position and the exact momentum of a particle at the same time. The more you know about one, the less you know about the other. But the principle goes deeper, applying to other pairs of properties, including energy and time. And this is where the universe starts getting really weird. The energy-time uncertainty principle means that for very, very brief moments, the energy in any given point in space can fluctuate wildly. It's as if the universe has a cosmic bank account, and for incredibly short periods, it allows tiny amounts of energy to be borrowed from nothing from the vacuum itself. This isn't just some quirky math. This borrowed energy can manifest as pairs of particles and antiparticles that spontaneously pop into existence, live for a fleeting moment, and then annihilate each other, paying back the energy debt so fast that no laws are broken on average. These are virtual particles. They're the ghosts in the machine of reality. Suddenly, the vacuum of space, once the definition of nothingness, was revealed to be a seething, effervescent sea of these phantom particles. Think of the fizz on a freshly poured soda. The bubbles rise and pop in a constant, roiling activity that comes from a seemingly placid liquid. According to quantum field theory, the vacuum of space is just like that. It's alive with these vacuum fluctuations. This isn't just speculation. It's a core prediction of our most successful theory of particles and forces, and it's been confirmed by experiment. So we have two pictures of reality. On one hand, Einstein's general relativity gives us a smooth, placid spacetime, like a calm lake. On the other, quantum mechanics tells us this lake is fizzing with the constant creation and annihilation of virtual particles. For a long time, this wasn't a huge problem. Gravity is incredibly weak on the scale of particles, and quantum effects are negligible on the scale of planets. The two theories could exist in their own domains, like two kingdoms that shared a border but rarely interacted. But physicists can't let a border like that stand. They're driven to find a single, unified theory that describes everything. They have to ask, what happens at that border? What happens when you try to apply both theories at once? What happens when you take Einstein's smooth spacetime and zoom in until the quantum fizzing can't be ignored? The answer is where our story takes a dark turn. The answer is that our theories completely and utterly break down. Where worlds collide. The Planck scale. Every map has a point where it says, "Here be dragons." For physics, that point is the Planck scale. It's a scale of measurement so small it's almost impossible to comprehend. The Planck length is about 10 to the power of minus 35 meters. That's a decimal point followed by 34 zeros and then a 1. A distance so small that if you scaled up an atom to the size of the known universe, the Planck length would be about the height of a tree. The Planck time is the time it takes light to travel that distance, an almost incomprehensibly brief instant of about 10 to the power of minus 43 seconds. This isn't just some random number. The Planck scale is woven from the fundamental constants of nature. the speed of light, Planck's constant from quantum mechanics, and the gravitational constant. It is the natural meeting point of our two great theories. It is where quantum mechanics and general relativity must finally confront each other. And when they do, our math predicts a catastrophe. Let's revisit our two conflicting ideas. Quantum mechanics says that for very short time intervals, energy can fluctuate dramatically. General relativity says that energy curves space-time, that's what gravity is. So, what happens at the Planck scale? The fleeting, high-energy virtual particles that quantum mechanics predicts should have enough energy to dramatically warp the space-time around them. The calm ocean of Einstein's universe, when viewed at this microscopic level, would become a raging, chaotic tempest. Space and time themselves would lose their meaning. The very geometry of reality becomes an irrepressible seething broth, to borrow a phrase from John Archibald Wheeler, the physicist who first envisioned this chaos in 1955. Wheeler gave this jittery state of space-time a name: quantum foam. He realized that at the Planck scale, space-time wouldn't be a smooth fabric. It would be a foam of roiling, fluctuating geometry. Tiny, virtual black holes could pop into existence and evaporate almost instantly. Microscopic wormholes could form and collapse in the blink of an eye. The smooth reality we experience would dissolve into a probabilistic storm where the very concept of a single location becomes fuzzy. This is the universe's ultimate theoretical glitch. It's a fundamental incompatibility message from the cosmos. It's as if the two master programs governing reality, general relativity and quantum mechanics, crash the entire system when run together at this fundamental level. This theoretical foam isn't just some localized phenomenon. It's the predicted foundation of everything. And this presents a terrifying paradox. If the bedrock of reality is this theoretically chaotic, why is the universe so stable? Why doesn't this microscopic storm of black holes and wormholes bubble up and wreak havoc? If our best theories predict this much chaos at the foundation, how is the universe running at all? The supposed existence of this quantum foam implies a puzzle. A universe that shouldn't be as stable as it is. For decades, this has haunted physicists. But slowly, a radical new idea began to emerge. An idea that this chaos wasn't a flaw at all. It was a feature. Just as the universe might rely on a hidden structure to stay stable, the creation of these videos relies on a foundation of support from you. Every subscription, comment, and share helps build the foundation that allows us to explore these fascinating subjects. If you're enjoying this journey into the weirdness of the cosmos, please consider subscribing. It costs you nothing, but it makes a world of difference to us, allowing us to keep exploring the biggest questions the universe has to offer. Thank you. Now, let's get back to the chaos that might just save us. Fingerprints of the foam. The proof in our world. The idea of a seething quantum foam might sound like pure science fiction. For a long time, it was treated as a purely theoretical, if deeply troubling, concept. The Planck scale is so small, so far beyond our experimental reach, that directly seeing this foam is likely impossible. But if the vacuum of space is truly alive with these quantum fluctuations, it should leave subtle, indirect fingerprints on the world we can measure. And it does. The first and most famous piece of evidence is the Casimir effect. In 1948, the Dutch physicist Hendrik Casimir imagined a simple experiment. Take two perfectly smooth, uncharged metal plates and place them parallel to each other in a perfect vacuum. Classical physics says nothing should happen. They're uncharged, in a vacuum, so they should just sit there. But Casimir realized the vacuum wasn't empty. It was filled with quantum fluctuations of all possible wavelengths. In the open space outside the plates, fluctuations of all sizes can exist. But in the narrow gap between the plates, only fluctuations with wavelengths that fit perfectly into the gap can exist. This creates an imbalance. There are more possible fluctuations on the outside than on the inside. This results in a greater vacuum pressure on the outside pushing in, creating a tiny but measurable force pushing the plates together. For decades, this was just a prediction. But in 1997, Steve Lamoureux managed to measure it, and his results matched Casimir's prediction to within 5%. Later experiments have improved this accuracy even more. The Casimir effect was real. The vacuum was not empty. It could exert a physical force, a push from nothingness, powered by quantum fluctuations. It was the first tangible hint of the quantum foam. But there's more. Another piece of evidence comes from the electron itself. According to early quantum theory, the electron should have a magnetic strength, or magnetic moment, of exactly 2. But when measured, the value is closer to 2.0023. Where does this tiny anomaly come from? It comes from the quantum foam. An electron is never truly alone. It's constantly interacting with the sea of virtual particles around it, emitting and reabsorbing virtual photons. This cloud of virtual activity changes the electron's properties. When physicists calculated all these interactions, their theoretical prediction for the electron's magnetic moment matched the experimental measurement to more than 10 decimal places. It's one of the most stunningly accurate predictions in all of science. So, the effects of the foam seem real. But this only deepens the mystery. We have proof the vacuum is an energetic place. Yet, observations from NASA's Fermi Gamma Ray Space Telescope, looking at light from distant quasars, show that spacetime is remarkably smooth. If it were excessively foamy, light would scatter over billions of light years, blurring the images. The sharp images we see allow scientists to set limits, showing that spacetime is smoothed down to scales far smaller than an atom. The foam is constrained, more well-behaved than the most extreme theories predicted. The chaos is there, but somehow, it's contained. So what's stopping it from crashing the system? The answer, it turns out, might be the glitch itself. The Great Cosmic Cancellation. We've arrived at the central paradox. A chaotic, fizzing quantum foam seems to underpin reality. This foam is a theoretical glitch where our best theories predict chaos. And yet, we have experimental hints that it exists, while astronomical observations tell us the universe is incredibly smooth. How can both be true? One fascinating idea lies in a concept that's both profound and simple. Averaging. Imagine standing in a torrential downpour. Individual raindrops hit you randomly. The experience is chaotic. But if you measure the total water falling on a large field over an hour, you get a very predictable, stable number. The chaos of the individual drops averages out to a smooth, consistent flow. Something similar might be happening with quantum foam. The violent fluctuations are all happening at once, everywhere. The thinking goes that for every region of spacetime violently expanding due to a fluctuation, another region next to it might be violently contracting. The ups and downs, the pushes and pulls, could all sum, with incredible precision, to almost zero when you zoom out. The chaos smooths itself out. This idea has been explored mathematically by physicists like Stephen Carlop. His work suggests that a foamy spacetime could be self-regulating. In this model, the enormous gravitational effects predicted at the Planck scale are hidden, because on any scale we can measure, they have already averaged to nearly nothing. It's like a perfectly balanced tug-of-war with trillions of hands pulling in every direction at once, with the net result that the central rope doesn't move at all. This self-canceling idea might also offer a potential solution to one of the biggest mysteries in physics: the cosmological constant problem. Quantum theory predicts a gigantic amount of energy in the vacuum. Plug this into Einstein's equations, and it should cause the universe to expand or collapse at a ludicrous rate. The prediction is about 120 orders of magnitude larger than what we observe, a discrepancy famously called the worst theoretical prediction in the history of physics. But what if the quantum foam is self-canceling? Perhaps the enormous positive energy predicted by quantum theory is perfectly counteracted by the enormous gravitational energy created by the foam's own curvature. In this scenario, the glitch of the quantum foam would be actively canceling out the glitch of the vacuum energy, leaving behind the tiny, almost zero value we actually observe. The foam wouldn't be breaking reality. It would be performing a delicate balancing act to keep it stable. This is a profound shift in perspective. The quantum foam might not be a bug in the system. It could be the system's error correction protocol. It could be the cosmic mechanism that takes the wild, nonsensical predictions from the clash of our physical laws and tames them, presenting us with the calm, stable universe we see. The universe's shock absorber. So, what's the final picture that's emerging? The universe, at its most fundamental level, might be built on a paradox. It could be simultaneously chaotic and orderly, unstable and eternal. And the quantum foam is the engine of this paradox. Think of it as the ultimate shock absorber. When you push a physical system to its limits to the Big Bang, or into a black hole, our laws of physics break. General relativity predicts singularities, points of infinite density. Quantum mechanics predicts infinite energies in the vacuum. These are the points where the smooth machine of the universe should shatter. But perhaps the quantum foam acts as a buffer. At these extremes, reality doesn't shatter, it just gets foamy. The energy doesn't become infinite. It gets churned into a froth of virtual particles and microscopic geometries that, on average, behave themselves. The foam could be the universe's built-in safety mechanism, the fail-safe that kicks in when other systems are overloaded. This theoretical instability at the smallest scales may be what grants stability to the largest scales. It's the give in the system that prevents it from breaking. The glitch isn't a problem to be fixed, it is the potential solution. The frantic, microscopic chaos could be the very thing that holds the placid, macroscopic cosmos together. We started with a strange thought, that the universe is built on a theoretical glitch that should make it unstable. We journeyed down to the smallest possible scales, where space-time may dissolve into a chaotic, seething foam, a storm of virtual particles and unimaginable energies. We saw how this concept, born from the clash of our two most successful theories, seemed to spell doom for a stable reality. But then, we saw the twist. We found fingerprints of this vacuum energy in our own world, in the subtle push between two plates and in the magnetic dance of an electron. We discovered fascinating new ideas suggesting this chaos may not be random but self-organizing, a great cosmic cancellation that averages out its own infinities and might even solve the greatest predictive failure in science. The ultimate glitch may be what saves the universe. The foam could be the cosmic error correction code, the shock absorber at the heart of reality that keeps the laws of physics intact. It's the paradox that allows for our existence. The universe may not exist in spite of this theoretical flaw. It may exist because of it. So the next time you look up at the serene and silent night sky, remember what might lie beneath. Remember that the stable ground you stand on, the air you breathe, and the stars you see could all be built upon an ocean of unimaginable, fizzing, furious chaos. A beautiful, perfect glitch in the fabric of space and time. If this exploration of cosmic paradoxes has expanded your sense of wonder, make sure you're subscribed and have notifications turned on. We have many more journeys to the edge of physics planned. And for those who want to support our explorations even further, consider joining our Patreon. You'll get access to exclusive content and become a crucial part of the team that makes these videos possible. The code that stops the universe from crashing. Somewhere in the source code of our universe, there's a fatal error. A line that just says, divide by 0. It's an operation so catastrophic, it threatens to crash reality itself. Physicists have a name for this error: a singularity. It's a point where the known laws of nature, the very rules that run space, time, and matter, simply break down. The equations we use to describe the cosmos just spit out the answer, infinity, which makes no physical sense at all. And according to our best theory of gravity, these cosmic crash points shouldn't just be possible, they should be everywhere. They should be at the heart of every black hole and at the very beginning of time. And yet, here we are. The universe is still running. The cosmos hasn't blue-screened. This is a huge paradox, and it suggests there's a hidden piece of code, some fundamental rule of nature that we're just not seeing. It hints that a cosmic censor is stepping in to stop the ultimate crash. This isn't just a quick patch. It's a clue that points to a deeper, more elegant program running underneath it all. And finding this hidden code, understanding what stops the universe from dividing by zero, could rewrite everything we think we know about reality. The glitch in the code. What is a singularity? To get what this cosmic glitch is all about, let's start with a simple spring. The physics of a spring is described by a beautiful little law called Hooke's law. It just says the force you need to stretch or compress a spring is proportional to how far you stretch or compress it. Simple, predictable, reliable. But every rule has its limits. If you rearrange the equation to solve for the spring's stiffness, you get force divided by distance. Now, what happens if you imagine compressing that spring to an infinitesimally small point? As the distance gets closer and closer to zero, the math tells you a wild story. The stiffness of the spring shoots towards infinity. But would that actually happen? If you took a real spring and squeezed it with unimaginable force, would it become infinitely resistant? Of course not. At some point, the atoms of the spring would get so close that the old rules of classical mechanics just wouldn't apply anymore. You'd step into the weird and wonderful world of quantum mechanics, where new rules take over. The atoms themselves would fight back against being forced into the same space. The equation wasn't wrong, it was just waving a white flag. That, infinity, wasn't a property of the spring. It was an error message from the theory, basically saying, my rules don't work here. You need a better program to understand what happens next. That is exactly what a singularity is in physics. It's not a place where the universe itself breaks, but a point where our description of the universe breaks. When the equations of Albert Einstein's general theory of relativity, our master code for gravity, predict that something like density or spacetime curvature becomes infinite, that's the universe sending us the same error message. It's a flashing red light on the dashboard of physics, telling us that our theory has been pushed too far and it's no longer the right tool for the job. For almost a century, we've been haunted by this glitch. General relativity is arguably the most successful theory ever created. It's a masterpiece that describes the graceful dance of planets, stars, and galaxies, painting a picture of space-time as a flexible fabric that gets warped by mass and energy. We experience that warping as gravity. The theory has passed every single test we've ever thrown at it with flying colors. And yet, buried in its own elegant math are the seeds of its destruction. These predictions of infinity. And they're not some rare, obscure edge cases. They show up in the two most important places imaginable. At the end of time inside a black hole, and at the very beginning of time for the universe itself. These are the cosmic crash sites, the places where our understanding of reality appears to divide by zero. The crash sites. Where the universe divides by zero. Our cosmic detective story has two primary crime scenes, two places where general relativity returns an answer of infinity. The first is a place of eternal darkness and unimaginable force, the heart of a black hole. Picture a star far more massive than our Sun. After millions of years, its nuclear furnace sputters and dies. The outward pressure that was fighting against its own gravity is gone. Gravity, the most relentless force in the cosmos, finally wins. In less than a second, the star's core collapses under its own staggering weight. The crush is so intense that protons and electrons are mashed together into neutrons. If the core is heavy enough, even the force that keeps neutrons apart gets overwhelmed. The collapse becomes unstoppable. As all that matter gets squeezed into a smaller and smaller space, its gravity intensifies. It warps the fabric of spacetime around it so badly that it creates a boundary, a one-way door called the event horizon. This isn't a physical surface, it's a point of no return. Anything that crosses it, a planet, a cloud of gas, even light itself, can never, ever escape. It's on a one-way trip to the center. And what's at the center? According to the perfect math of general relativity, the answer is a singularity. All the mass of that giant star, plus everything that's ever fallen in, gets crushed into a point with zero volume and literally infinite density. Space-time curvature becomes infinite. Our very ideas of space and time get twisted into a pretzel. In fact, inside the event horizon, space and time actually trade places. The direction, forward, no longer points to the future. It points directly at the singularity. You can no more avoid hitting the singularity than you can avoid next Tuesday. It's not a place you can steer around. It becomes your future. At this point, the laws of physics as we know them just stop working. The theory goes silent. It has crashed. That's our first fail error. But there's an even bigger one. It's not a place you can point to, because it's the moment the entire sky was born. It's the origin of our universe, the Big Bang. We live in an expanding universe. We see distant galaxies racing away from us in every direction. That's the story of the last 13.8 billion years. But if we rewind that story, all those galaxies, all the matter and energy in the cosmos, come rushing back together. The universe gets smaller, denser, and hotter. If you run the equations of general relativity all the way back, they tell you that this cosmic rewind continues until everything, the entire observable universe, is crushed into a single, infinitesimally small point. The Big Bang singularity. A state of infinite temperature and infinite density at time zero, the very beginning of time itself. Here, the problem is even bigger than in a black hole. A black hole singularity is a place in spacetime. The Big Bang singularity is the origin of spacetime. Asking, what came before the Big Bang, is like asking, what's north of the North Pole? The framework for an answer just doesn't exist. Our entire cosmic origin story starts with a division by zero error. It begins right where our best laws of physics fail. For a long time, physicists just hoped these infinities were mathematical ghosts, not something real. The inevitability engine. The detective who proved the crash was no accident. Back in the mid-20th century, a lot of physicists figured that singularities were just an illusion. They thought the math only predicted them because we were oversimplifying things, assuming a star collapsed in a perfect, neat sphere. But the real universe is messy. Stars spin, they wobble, they're lumpy. The thinking was that in a realistic collapse, all the matter wouldn't hit a single point. It would swirl around and miss the center, settling into some super dense but ultimately finite state. The singularity, they hoped, would just be avoided. The crash wasn't a feature of the code. It was a bug caused by using idealized scenarios. Then, in 1965, a mathematical physicist at Oxford named Roger Penrose came along. Penrose, our story's brilliant detective, wasn't so sure. He attacked the problem from a totally new angle. Instead of getting lost in the messy details of collapsing stars, he focused on something much cleaner: the behavior of light in a strong gravitational field. His work, which would eventually win him a Nobel Prize, proved that singularities weren't an accident. They were an inevitable feature of general relativity. Penrose's key insight was a concept he called a trapped surface. Imagine you set off a flash of light in empty space. The light expands out in a sphere. Now, do the same thing near a massive star. Gravity will bend the light's path, but the sphere of light will still expand outwards. But Penrose asked, what if gravity got so strong that it could actually overpower the light's expansion? He imagined a closed surface where both the outward pointing light rays and the inward pointing ones are actually forced to converge. Think about that. Even the light that's trying to escape is getting dragged back in. The surface area of this sphere of light can only shrink. It can never grow. That is a trapped surface. And once a trapped surface forms, Penrose proved with pure mathematical logic, a singularity isn't just possible, it's unavoidable. As long as gravity pulls things together, which it does, those converging light rays have to meet somewhere. And since nothing can travel faster than light, any matter trapped inside that surface is also doomed. It's all getting funneled down to a point where the theory breaks. The power of Penrose's theorem was that it didn't care about the messy details. It didn't matter if the star was spinning or shaped like a cosmic potato. If the collapse was strong enough to form a trapped surface, which happens when an event horizon forms, a singularity had to happen. That was the rule. This was a bombshell. Penrose had just shown that the division by zero error wasn't a bug you could patch with a dose of realism. It was a feature, hard-coded right into the operating system of gravity itself. The problem was much deeper than anyone had realized. Our best theory of gravity was predicting its own downfall under conditions that are common all over the universe. But there was a loophole. Penrose's theorem proved a singularity must form, but it didn't say anything about where it would be. Specifically, it didn't guarantee it would be safely hidden behind an event horizon. And that opened the door to a possibility far more terrifying than a black hole. A possibility that could corrupt the entire system. The cosmic censor. The hidden code that prevents a system-wide crash. So, Penrose's theorem made singularities a fact of life for our theory of gravity. But it left a terrifying question hanging in the air. Do these points of infinite chaos always have to be locked away behind an event horizon? What if a singularity could form out in the open, where we could see it? This chilling idea is called a naked singularity. To get why this is a total nightmare, you have to understand what a singularity really is. It's a point where the laws of physics, the very idea of cause and effect, are just deleted. If a singularity were naked, we could theoretically look at a place where predictability completely breaks down. Anything could pop out of it, for no reason at all. A teacup. A supernova. A perfect copy of Hamlet. It would be a wound in the fabric of reality, bleeding pure, unfiltered chaos into the cosmos. The whole idea that the future is determined by the present would be shattered. If you can't predict what's coming out of a naked singularity, you can't really predict anything with certainty. The universe would stop being a cosmos, an ordered, understandable system, and would just become chaos. The code wouldn't just crash in one spot. The whole operating system would get corrupted. Faced with this awful possibility, Penrose and others proposed an elegant solution. They came up with a new principle of nature, a rule that isn't written in Einstein's equations but one the universe seems to follow. They called it the cosmic censorship hypothesis. Basically, it's a guess that says nature hates a naked singularity. This hypothesis comes in two flavors. The weak cosmic censorship hypothesis is the modest one. It says any singularity that forms from a realistic collapse, like a star, has to be hidden from anyone looking from far away. In other words, every singularity has to wear an event horizon. The universe practices a form of cosmic decency, shielding us from its most bizarre and unpredictable parts. The crash is contained inside a black box, a quarantine zone that prevents the chaos from getting out. But then there's the more ambitious version, the strong cosmic censorship hypothesis. This one goes way further. It says no observer should ever be able to see a place where predictability breaks down. This even applies to a brave astronaut who decides to dive into a black hole. The strong hypothesis suggests that the singularity predicted by classical physics isn't something you could ever actually reach. As you get closer, some new law of physics, some deeper piece of reality, must step in and prevent the infinity from ever forming in the first place. Think of it like a cosmic firewall. The weak version says the firewall detects the divide by zero error and immediately quarantines it. The strong version says the firewall doesn't just quarantine the error, it actively solves it, replacing the bad code with something that works before it can even run. For decades, this idea has been a bedrock of physics. It's a belief that the universe is, at its core, rational. But it's also admitting we don't know what's going on. Just hiding the error doesn't fix it. It's a workaround that lets the program keep running, but it doesn't solve the fundamental glitch in the code. To really solve the problem, we can't just censor the singularity, we have to understand it. And to do that, we have to go beyond Einstein and into the strange, uncharted territory of quantum gravity. If you think cosmic firewalls and hidden laws of physics are as cool as I do, take a second to subscribe. We dive into mysteries like this every week, and your support helps us keep searching for these incredible answers. The Code Patch. Writing the new laws of physics. Okay, so our investigation has led us here. Our best theory of gravity, general relativity, has a division by zero error that creates singularities. We have a proposed firewall, cosmic censorship, that hides the error to keep the rest of the universe safe. But that feels unsatisfying. It's like sweeping a huge problem under the rug. Hiding an infinity doesn't make it go away. It just makes us ask, what is really going on in there? To find the answer, let's go back to our spring. When we tried to crush it down to an impossibly small size, our simple law crashed. The fix wasn't to put a warning label on the equation, it was to boot up a whole new operating system, quantum mechanics. Quantum mechanics is the code that runs the universe on the smallest possible scales. And one of its key features is a kind of built-in fuzziness. You can never know the exact position and the exact momentum of a particle at the same time. This natural uncertainty prevents the kind of infinite sharpness that leads to singularities. This is the crucial clue. The singularity happens because general relativity is a classical theory. It treats everything as smooth and continuous. But at its core, the universe isn't classical. It's quantum. To resolve the singularity, we need to merge general relativity with quantum mechanics. We need a theory of quantum gravity. This is the holy grail of modern physics. We don't have a complete theory yet, but we have a couple of amazing candidates for the universe's true source code. Our first candidate is string theory. String theory has this radical, beautiful idea. If you could zoom in on any particle, you wouldn't see a point. You'd see a tiny, vibrating, one-dimensional loop of energy, a string. All the different particles we see are just different notes, different ways these fundamental strings can vibrate. So how does this fix the singularity? Crucially, these strings are not infinitely small. They have a minimum size, known as the Planck length. Because the basic building blocks of the universe have a size, you can no longer crush matter into a point of zero volume. In the heart of a black hole, the strings would vibrate more and more frantically, but they would never, ever reach zero size and infinite density. The division by zero error is avoided because the denominator can never actually hit zero. The singularity is just gone. It's smeared out by the fuzziness of the strings, replaced by some bizarre, super dense state of stringy matter we don't fully understand yet. Our second leading candidate, loop quantum gravity, takes a completely different approach. Instead of focusing on the particles, it focuses on spacetime itself. In this theory, the fabric of spacetime isn't a smooth sheet. It's a network, a weave of discrete, indivisible quantum loops. Space itself is made of atoms, or pixels, of volume, each one unimaginably tiny. This has a huge consequence for singularities. If space is made of indivisible chunks, you simply can't squeeze something into a volume smaller than one of those chunks. Gravity can get insanely strong, but it can never become infinitely strong, because there's a smallest possible distance. The singularity is resolved because the stage it was supposed to perform on a smooth, infinitely divisible spacetime doesn't actually exist. And this leads to one of the most mind-bending ideas in all of science, the Big Bounce. In loop quantum gravity, the Big Bang might not have been a beginning at all. It could have been a bounce. A previous universe might have existed, one that expanded and then eventually collapsed back in on itself. As all its matter crushed together, it didn't hit a singularity. Instead, when the density hit the absolute maximum allowed by the pixels of spacetime, a powerful new repulsive force, a purely quantum effect of gravity, kicked in, stopping the collapse and causing the universe to rebound explosively. Our Big Bang wasn't a beginning. It was the moment of that bounce, a violent transition from a prior, contracting universe into our own. The universe isn't crashing, it's upgrading. So, we come back to where we started. The fatal error in the cosmic code. What we've found is that the division by zero error was never a flaw in the universe itself. It was a flaw in our understanding of it. The singularities from general relativity aren't cosmic dead ends where physics gets destroyed. They are signposts, pointing the way to a deeper reality. They are the exact spots where the classical description of gravity has to pass the baton to a quantum one. The code that stops the universe from crashing isn't a simple firewall. It's an entire new operating system, a theory of quantum gravity that replaces Einstein's smooth world with a fuzzy, pixelated, quantum world of strings or loops. The infinities disappear because, at the deepest level, the universe has a finite resolution. It seems nature has its own built-in protection against the absurdity of infinity. The search for this ultimate code is the greatest challenge in physics today. The clues, the singularities, are telling us that the two great theories of the 20th century, general relativity and quantum mechanics, are just two parts of a single, grander story. We're like archaeologists who found two halves of a Rosetta Stone, and we're now trying to figure out the language that unifies them. The fatal error wasn't in the cosmos, but in our assumption that we had the final version of its source code. These breakdowns in our laws aren't failures. They're the engine of discovery. They show us the limits of our knowledge and dare us to look past them. They're the moments where the universe isn't crashing, it's revealing that our understanding needs an upgrade. What do you think? Is the universe made of strings, loops, or something we haven't even dreamed of yet? Let me know your thoughts in the comments. And if you enjoyed this trip to the edge of physics, please consider subscribing and sharing this video. Black holes don't break physics, they reveal its deepest secret. At the very heart of a black hole, reality as we know it breaks. All the laws of physics that govern our cosmos, from a feather drifting in the wind to the grand dance of galaxies, they all just shatter into a point of infinite chaos. For 100 years, we've looked at this as a failure in our understanding. A cosmic dead end where our math just screams and our best theories crumble into dust. But what if it's not a failure? What if it's a message? I'm going to argue that black holes don't break physics at all. They're more like signposts, pointing us toward the hidden laws that truly run the show. The exact point where our theories fall apart is the starting line for a deeper truth about our universe. This breakdown isn't an ending. It's an invitation to find the next, more profound layer of reality. So stick with me, because by the end of this, you'll see that these cosmic monsters aren't here to break the rules. They're here to show us how the game is really played. The clockwork universe and its first cracks. To really get why black holes are such a profound challenge, we first need to appreciate the beautiful structure they seem to threaten. For over 200 years, our picture of the universe was shaped by one man, Sir Isaac Newton. Newton gave us a clockwork universe. Back in the late 17th century, he handed us laws of motion and a law of universal gravitation that were, for all intents and purposes, perfect. His equations painted a picture of a world with beautiful, predictable certainty. A force acts on an object, it accelerates. For every action, an equal and opposite reaction. Gravity was this invisible string tying everything together across the cosmos, its strength depending only on mass and distance. With Newton's laws, we could predict the arc of a cannonball, the ocean tides, and the majestic orbits of the planets. His physics was so powerful that when astronomers saw wobbles in the orbit of Uranus, they didn't doubt the laws. They used them to predict a whole new planet, Neptune. And bam, they were right. Newton's universe was deterministic. If you knew where every particle was and where it was going, you could, in theory, calculate the entire future and past of the cosmos. It was a universe with a fixed, unchanging stage of absolute space and time. For 2 centuries, this was physics. It worked. It was elegant. It felt finished. But it wasn't. The first crack in this perfect machine didn't come with a bang, but with a flicker of light. See, Newton's world had no speed limit. But as the 19th century rolled into the 20th, scientists were struggling with the weirdness of light. Experiments, most famously by Michelson and Morley, showed something completely baffling. The speed of light in a vacuum is always the same. It doesn't matter if you're flying toward a flashlight or speeding away from it. You'll always measure its light hitting you at the exact same speed, about 300,000 kilometers per second. This makes zero sense in Newton's world. If you're on a train going 100 kilometers an hour and throw a ball at 20, someone on the platform sees it moving at 120. Simple. But light just refused to play along. If you're on a spaceship at half the speed of light and turn on your headlights, the light doesn't move away from you at half its normal speed. It still zips away from you at the asterisk full speed of light. This paradox was a deep wound in classical physics. It was a sign that Newton's seemingly perfect laws had their limits. They worked great for our everyday world, but at the extreme speeds of light, they just broke down. The person who fixed this was, of course, a young patent clerk named Albert Einstein. In 1905, his theory of special relativity took the constant speed of light not as a paradox, but as a rule. He basically said, the speed of light is the ultimate cosmic speed limit. And from that one radical idea, everything changed. If the speed of light has to be the same for everyone, then something else has to be flexible. And that something, Einstein showed, was space and time itself. They aren't the rigid, separate things Newton thought they were. They're woven together into a single fabric, space-time. The faster you move through space, the slower time ticks for you relative to someone standing still. That's time dilation. Mass and energy? Just 2 sides of the same coin, with the famous equation E equals mc squared. This gave us our first big lesson. When a physical law seems to break, it's usually because we've pushed it to an extreme where a deeper law takes over. Newton's laws weren't wrong, they were just an incredibly good approximation of a deeper truth. Special relativity didn't junk Newton's physics. It put a frame around it, revealing the bigger picture. But Einstein wasn't done. He dealt with high speeds, but there was a bigger problem: gravity. According to Newton, gravity was an instantaneous force. If the sun vanished right now, Earth would instantly fly off its orbit. But special relativity had just proven that nothing, not even information, can travel faster than light. The news of the sun's disappearance couldn't reach us for at least 8 minutes, the same time it takes for its light. Newton's gravity was now fighting with Einstein's own new theory. The clockwork universe was facing an even bigger crisis. Einstein knew his work wasn't done. He had to completely rewrite the law of gravity. This decade-long struggle would lead to his masterpiece, and to the very cosmic monsters we're talking about today. The ultimate breakdown. General relativity and the singularity. Einstein started with what he called the happiest thought of his life. He pictured a man falling from a roof. While falling, that man would feel weightless. If he dropped an apple, it would just float right next to him. In his own little bubble, gravity would have seemingly vanished. From this simple idea, Einstein forged a revolution. Gravity is not a force. What we feel as gravity, Einstein proposed in his 1915 general theory of relativity, is just the curvature of spacetime. Think of spacetime as a stretched rubber sheet. If you put a bowling ball on it, it creates a deep curve. Now, if you roll a marble past it, the marble isn't pulled by some mysterious force. It's just following the curve in the sheet. It's taking the straightest possible path through a curved space. That, Einstein said, is gravity. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. The Earth isn't being pulled by the sun. It's just following a straight path through the spacetime that the sun has warped. Even time is affected. Time actually runs slower in stronger gravitational fields. This isn't just theory. Your GPS has to correct for the fact that time is ticking slightly faster for the satellites in orbit than for us on the ground. Without Einstein's corrections, your GPS would be useless in minutes. General relativity was a massive success. It explained a tiny wobble in Mercury's orbit that Newton's laws couldn't. It predicted starlight would bend around the sun, which was confirmed during a 1919 eclipse, making Einstein a global superstar. And 100 years later, in 2015, we directly detected ripples in spacetime gravitational waves from two colliding black holes. Einstein's theory has passed every single test we've ever thrown at it. And yet, buried inside its own beautiful math, Einstein found something monstrous. His equations didn't just allow for black holes. They practically screamed that they must exist. Take a star way bigger than our sun. For billions of years, it's in a delicate balance. The outward push of nuclear fusion in its core holds back the crushing force of its own gravity. But when the star runs out of fuel, the furnace shuts down. Gravity wins. In a massive supernova explosion, the star's outer layers are blown away. But the core, if it's heavy enough, just collapses. And collapses. And keeps collapsing. General relativity says if you squeeze enough mass into a small enough space, the curvature of spacetime becomes so extreme it basically ties itself in a knot. It creates a region where gravity is so strong that nothing, not even light, can get out. This point of no return is called the event horizon. It's a one-way door in the universe. You can go in, but you can never come out. To someone watching from the outside, you would appear to slow down as you fell in, your image getting redder and dimmer, frozen for eternity right at the edge. But for you, the unfortunate traveler, you'd cross that boundary and be sealed off from the rest of reality forever. But what happens inside? At the very center? This is where Einstein's elegant equations give us their most terrifying prediction. They say the collapse doesn't stop. All the mass of a star millions of times the mass of Earth gets crushed into a space with zero volume. The density becomes infinite. The curvature of spacetime becomes infinite. This is a gravitational singularity. And at this point, general relativity, our best theory of gravity, completely breaks down. All the laws of physics stop making sense. The equations don't give you answers, they just give you infinities. And infinity isn't a real thing. It's the sound of math screaming at us that the theory has been pushed too far and has failed. This is the ultimate breakdown. It's a catastrophic failure of our description of reality. It's as if there's a hole, not just in space, but in the very logic of physics itself. And for a long time, this is where we were stuck. We have general relativity, which is perfect for the big stuff. But we have another theory, just as powerful, that's perfect for the small stuff. And when these two great theories meet in the heart of a black hole, they go to war. That other theory is quantum mechanics. It describes the world of atoms and particles, a fuzzy world of probabilities and bizarre connections. Where general relativity is smooth and predictable, quantum mechanics is chunky and weird. In the quantum world, particles can be in multiple places at once and pop in and out of thin air. Most of the time, this isn't a problem. Gravity runs the world of stars and galaxies, and quantum mechanics runs the world of atoms. They stay in their own lanes. But a black hole is the one place where they're forced to meet. A singularity is both unbelievably massive, general relativity's turf, and infinitesimally small, quantum mechanics' turf. It's the shotgun wedding of our two greatest theories. And their union is not a happy one. The clash between them creates a paradox so deep it's kept physicists up at night for 50 years. It's called the information paradox, and it's our first big clue that the breakdown of physics isn't an end, but a beginning. The cosmic detective story. The information paradox. For a while, scientists figured the singularity was just a weird math problem. After all, it was hidden behind an event horizon, so its lawless chaos was safely locked away. What happens in a black hole stays in a black hole. Right? Well, in 1974, a young Stephen Hawking discovered something that changed everything. By applying the strange rules of quantum mechanics to the edge of an event horizon, he found something that should be impossible. Black holes aren't completely black. They glow. According to quantum mechanics, even empty space is a bubbling soup of virtual particles that pop into existence in pairs, then almost instantly cancel each other out. But Hawking realized that if a pair of these particles appears right on the edge of an event horizon, one can fall in while the other escapes. The particle that escapes flies off as real, detectable energy. To an outside observer, it looks like the black hole is slowly radiating heat. This is now called Hawking radiation. This was a massive discovery. It means black holes aren't eternal prisons. They have a temperature, and they slowly evaporate over trillions upon trillions of years, until they eventually disappear in a final puff of radiation. But in solving one mystery, Hawking created a much, much bigger one. The black hole information paradox. Here's the problem. One of the most sacred laws in all of physics is that information can never be destroyed. In physics, information is the unique quantum data that makes up an object. It's the blueprint that distinguishes a star from a spaceship, or an encyclopedia from a lump of coal. This rule guarantees that you can always trace the present back to the past. You can scramble information, like burning a book, but in theory, if you collected every single particle of smoke and ash, you could piece the original book back together. Information is always conserved. So, let's throw that encyclopedia into a black hole. Its information falls past the event horizon, destined, according to general relativity, to be crushed out of existence at the singularity. For a while, physicists could just say, well, the information isn't gone, it's just locked inside. But Hawking radiation changed the game. The black hole evaporates. And Hawking's original math showed that the radiation coming out is completely random. It contains zero information about what fell in. So, when the black hole is completely gone, what happened to the information that made up the encyclopedia? Is it gone forever? If it is, then quantum mechanics, the foundation of modern physics, is wrong. If it's not, then general relativity or our understanding of black holes has to be wrong. This is the paradox. Our two most successful theories give us completely different answers. They can't both be right. This is a giant, flashing neon sign pointing directly at the spot where our understanding of the universe is broken. It tells us that the simple picture of a black hole with a single point at its center must be wrong. The breakdown isn't real. It's an illusion created by our incomplete theories. Physicists are cosmic detectives, and this is the ultimate cold case. For decades, they've been proposing mind-bending solutions. Maybe the information is subtly encoded in the Hawking radiation in a way we just don't understand yet. Or maybe the information never really falls in at all, but gets imprinted on the surface of the event horizon. This last idea led to one of the most staggering concepts in modern physics: the holographic principle. It suggests that all the information inside a 3D volume of space like a black hole can be fully described by the physics on its 2D boundary, the event horizon. It's like a hologram, where a flat surface encodes a full 3D image. If this is true, the information is never lost. It's smeared across the horizon and slowly returned to the universe. Another, even wilder idea called R equals EPR suggests that the spooky quantum connection between two particles is literally a tiny wormhole connecting them through spacetime. This would mean that the very fabric of spacetime is woven from quantum entanglement, and the information that falls into a black hole might stay connected to the outside world through these quantum threads. We don't know which of these ideas, if any, is right. But they are all forcing us to rethink the very nature of space, time, and information. And they all point in the same direction. We need a new theory. A deeper theory. A theory of quantum gravity. The revelation. A theory of everything. And this brings us to the heart of the matter. The singularity where physics breaks, and the paradoxes that come from it aren't failures. They are the most powerful tools we have. They are the crucibles where the next revolution in physics is being forged. They're pointing the way to the holy grail of physics, a unified theory of quantum gravity. A theory of everything would unite general relativity and quantum mechanics into a single framework, describing all the forces of nature with one set of laws. Black holes are telling us this isn't just a dream. It's a necessity. So what would a theory of quantum gravity look like? And how would it fix the singularity problem? While we don't have the final answer, there are two big ideas: string theory and loop quantum gravity. String theory says the fundamental building blocks of the universe aren't particles, but tiny, vibrating strings of energy. Different vibrations create different particles. In this picture, you can't have a singularity because strings aren't infinitely small points. You can't crush matter into zero volume because you'd just be crushing a ball of strings. Some models, like the fuzzball idea, suggest a black hole has no singularity at all. It's just a giant, messy ball of strings, and the information that falls in gets woven into the fuzz. Loop quantum gravity takes a different route. It suggests spacetime itself is made of discrete, indivisible chunks. It's like a digital image. If you zoom in far enough, you see the pixels. In this theory, you can't have a singularity because you can't crush something into a space smaller than a single atom of spacetime. Instead, as matter collapses, it would hit a maximum density and then bounce. The singularity is replaced by a Planck star, or a spacetime bounce. The breakdown is avoided. What's so incredible is that both of these leading theories, born from the very conflict that black holes represent, naturally get rid of the singularity. They replace the infinite chaos with new, predictable physics. They show us that the breakdown was never a feature of the universe, it was just a blind spot in our old theories. This is the deepest secret that black holes reveal. They are nature's ultimate laboratory. They are the one place where gravity is so intense and the scales are so small that the effects of quantum gravity become mandatory. They are showing us, in the most extreme way possible, the exact seams in our understanding of reality. The journey into a black hole starts with a sense of dread, a fall toward a place where everything is destroyed. We started with Newton's perfect clockwork universe, watched it give way to Einstein's warped spacetime, and then saw Einstein's own theory predict its own doom at an impossible point of infinity. We saw this breakdown create paradoxes that threatened to tear down the laws of physics. But we've come to see that this point of failure isn't an abyss. It's a lens. It's focusing all the biggest tensions in modern physics onto a single point and forcing us to solve them. Black holes aren't breaking physics. They are stress testing it. They're showing us exactly where our knowledge ends and where the next great adventure has to begin. The singularity isn't an answer, it's a question. The information paradox isn't a contradiction, it's a clue. They're the catalysts for a revolution, pushing us toward a unified theory of everything. They're teaching us that the universe is layered like a Russian doll. Newton's laws are inside Einstein's laws, and Einstein's laws will one day be found inside a deeper, more fundamental theory. Each time a law breaks, it's just a sign that we've found a larger, more encompassing one. So the next time you look at the night sky and think about these dark, silent behemoths, don't think of them as destroyers. Think of them as guides. They are the greatest puzzle in the cosmos, and in their darkness, they are lighting the way forward. They're revealing the deepest secret of all, that the laws of physics never truly break. They just lead us to grander, more beautiful truths about our extraordinary universe. What other cosmic mysteries keep you up at night? The Fermi paradox? Dark energy? Let us know in the comments below. And if you enjoyed this trip to the edge of reality and back, make sure to subscribe and hit the bell so you don't miss our next dive into the deepest secrets of the cosmos. The universe is trapped inside its own rules. What if the one place in the universe where all the rules seem to shatter is actually the place where they are most unbreakable? Picture yourself at the edge of a black hole, that point of no return where gravity is so intense that nothing, not even light, can get away. It feels like an error in the cosmic code, right? A place where physics just gives up. But it's not. This isn't the universe failing. This is the universe defining itself in the most extreme way you can imagine. For centuries, we've been uncovering the laws that run our reality, from an apple falling off a tree to the cosmic ballet of galaxies. But we've also found their limits, points where the rules seem to crack under pressure. At the speed of light, time slows to a crawl and space gets squished. At the heart of a black hole, our math just screams infinity and stops making sense. It's so tempting to see these as bugs in the system. But today, we're going to see why that's the wrong way to look at it. We'll discover that these so-called broken rules are actually the invisible scaffolding holding our entire universe together. We'll see how the cosmos is fundamentally inescapable, held in check by the very laws that seem to fracture at their most extreme. You're about to find out why the universe can never break its own rules, and why that's the most important thing about our existence. The comfort of everyday rules. Our story starts not in the chaos of the cosmos, but right here, in the comforting, predictable world we all live in. A world governed by rules so reliable that for over 200 years, we thought we had it all figured out. These are the laws of motion, first written down by Sir Isaac Newton back in the 17th century. Think about your morning coffee. You put your mug on the table and it just sits there. It doesn't start floating away or randomly slide off the edge. You've just witnessed Newton's first law. An object at rest stays at rest, and an object in motion stays in motion. It's the law of inertia. That mug has mass, and because it has mass, it's lazy. It wants to keep doing exactly what it's already doing, which, thankfully, is nothing. Now, give it a little nudge. A gentle push makes it slide a bit. A hard shove sends it flying. That's Newton's second law. To get something moving, you have to push it, and the heavier it is, the harder you have to push. It's why you can kick a soccer ball across a field, but you probably shouldn't try to do the same thing to a car. The car has way more mass, which means more inertia, and it takes a much bigger force to change its state of blissful rest. The simple equation for this, F equals ma, is one of the most powerful ideas in all of physics, explaining everything from a falling apple to the moon's orbit around the Earth. Finally, as your hand pushes that mug, you feel it push back against your fingers. That's Newton's third law. For every action, there is an equal and opposite reaction. When you push the mug pushes you back with the exact same force. You feel it, but because you have a lot more mass and you're stuck to the floor, you don't go flying backward. But the principle is absolute. It's how a rocket launches into space. It shoves exhaust down, and the exhaust shoves the rocket up. It's how you swim. You push water backward, and the water pushes you forward. For centuries, these three laws were the bedrock of physics. They were simple, they were elegant, and they just worked. They let us predict the path of a cannonball, build engines, and chart the courses of the planets with stunning accuracy. We lived in a clockwork universe. A grand, predictable machine where, if you knew where everything was and how it was moving, you could predict the entire future of the cosmos. This Newtonian world is the one we feel in our bones. It's solid and dependable. Time, in this view, is a universal clock, ticking at the same rate for everyone, everywhere. Space is just a fixed, unchanging stage. An inch is an inch, and a second is a second, no matter what. But this cozy, clockwork reality was about to be completely upended. As we started asking bigger questions and building better tools, we started poking at the edges of this Newtonian paradise. We asked, what happens when you push these rules to the absolute limit? What happens when you travel not at the speed of a horse, but at the speed of light itself? It was there, at that impossible velocity, that the first cracks in our perfect clockwork universe started to show. And it turned out, the rules weren't wrong. They were just incomplete. The first crack. The cosmic speed limit. Newton's clockwork universe was the champion for over 200 years. It seemed unassailable. But at the dawn of the 20th century, a young patent clerk in Switzerland named Albert Einstein was bothered by a tiny little inconsistency. The problem was where Newton's laws of motion met the laws of light. In Newton's world, speeds just add up. If you're on a train going 100 miles per hour and you throw a ball forward at 20 miles per hour, someone on the ground sees the ball moving at 120. Simple, intuitive, and for our everyday world, totally correct. But the laws of electromagnetism, which describe how light works, predicted something really weird. The speed of light in a vacuum, a constant called c, was always the same. Roughly 186,000 miles per second. It didn't matter if you were racing toward the light source or running away from it. You would always measure its speed to be c. This was a head-on collision of ideas. How could the speed of light be absolute if all other speeds were relative? So, Einstein made a wild gamble. What if the theory of light wasn't wrong? What if Newton's ideas about absolute space and time were? In 1905, he published his theory of special relativity, based on two powerful ideas. First, the laws of physics are the same for everyone. Second, the speed of light is the same for everyone. When you accept those two ideas, the consequences are mind-bending. If the speed of light has to stay constant, then something else has to be flexible. That something else, Einstein realized, was space and time. Imagine you're on a spaceship going 99% the speed of light. To you, everything feels normal. Your clock is ticking just fine. But to someone watching you from Earth, something bizarre is happening. They would see your clock ticking much, much slower than theirs. This isn't a trick. Time itself is literally running slower for you. The faster you move through space, the slower you move through time. At the same time, that observer on Earth would see your spaceship as being squished, shorter in the direction you're moving. Space itself contracts to make sure the speed of light stays constant for everyone. And most famously, Einstein revealed that mass is just a super-concentrated form of energy, giving us E equals mc squared. As you get closer and closer to the speed of light, your mass effectively increases, and it takes more and more energy to speed you up. To actually reach the speed of light, you'd need an infinite amount of energy. It's impossible. This is the cosmic speed limit. It's not a technological hurdle we can one day overcome. It's a fundamental rule woven into the fabric of spacetime. Trying to break the speed of light isn't like trying to build a faster car. It's like trying to draw a four-sided triangle. The very concept is a contradiction. So, the rule didn't break. It just revealed that it was part of a much bigger, stranger rule. Newton's laws are a fantastic approximation for the slow-moving world we live in. But when you ramp up the speed, the full, weird reality of relativity takes over. And this speed limit isn't just some arbitrary rule. It's the ultimate guardian of cause and effect. If you could travel faster than light, you could arrive somewhere before you left. You could see an effect happen before its cause. The universe protects itself from these paradoxes by making the speed of light an absolute, unbreakable barrier. We thought we were playing checkers, but Einstein showed us we were playing chess on a dynamic, four-dimensional board called spacetime. And this was just the beginning. Einstein's next step would take him from the rules of speed to the very nature of gravity, leading us straight to the most mysterious objects in the entire universe. The second crack: the nature of gravity. After rewriting the rules of space and time, Einstein spent the next 10 years wrestling with the big one his theory had left out: gravity. Newton saw gravity as an invisible, instantaneous force pulling between two objects. But instantaneous was now a dirty word. Special relativity said nothing could travel faster than light. If the sun just vanished, Newton's theory said the Earth would instantly fly off into space. But Einstein's theory demanded that the news of the sun's disappearance couldn't reach us any faster than light, which takes about 8 minutes. This conflict led Einstein to an even more profound idea. In 1915, he gave us his masterpiece, the theory of general relativity. In this new picture, gravity isn't a force at all. It's the shape of spacetime itself. The classic analogy is a good one. Think of spacetime as a big, stretched-out rubber sheet. If you put a heavy bowling ball in the middle, the sheet curves and warps. That curvature is gravity. Now, if you roll a little marble nearby, it will try to go in a straight line, but it's forced to follow the curve made by the bowling ball. That's the Earth orbiting the Sun. The Sun's enormous mass is bending spacetime, and the Earth is just following the straightest possible path through that curve. As the physicist John Wheeler put it, spacetime tells matter how to move, matter tells spacetime how to curve. This new vision of gravity made shockingly accurate predictions, like a tiny wobble in Mercury's orbit and the way starlight bends around the Sun, famously proven during a solar eclipse in 1919. General relativity was a huge success. But hidden inside its own equations was a prediction so strange that even Einstein hated it. The theory said that if you cram enough mass into a tiny enough space, the curvature of space-time would become so extreme that it would basically break. The gravitational pull would be so strong that the speed you'd need to escape would be faster than the speed of light. And since nothing is faster than light, nothing could escape. You'd have a black hole. Around this point of no return is a one-way door called the event horizon. Think of it as the lip of a cosmic waterfall. Outside of it, you can still get away if you have a powerful enough engine. But the second you cross it, no matter which way you turn, no matter how hard you fire your rockets, every single path you can take leads to one place. The center. It's not a wall you'd hit. It's a point in space-time where the future has only one destination. And what's at that destination? According to the theory, all that mass gets crushed into a point of zero size and infinite density is singularity. Here, the equations of general relativity just stop working. They spit out answers like infinity, which is physics speak for we have no idea what's going on. The known laws of physics cease to apply. This looks like the ultimate breakdown, the point where the universe finally shatters its own rulebook. For decades, physicists thought singularities were just a weird math error that couldn't happen in the real world. But the evidence for black holes just kept piling up. The singularity doesn't mean the universe is broken. It means our theory is broken. It's a giant, flashing arrow pointing to where a new, deeper theory is needed. General relativity is the law of the very big. But the singularity is a place where the very big is crushed into the realm of the very small. To understand it, we need a theory of quantum gravity. So once again, what looks like a broken rule is really just a handover. Just like Newton's laws passed the baton to relativity at high speeds, general relativity seems to pass the baton to a new theory at the center of a black hole. And to see what that theory might be, we have to dive into the bizarre, fuzzy world of the quantum. The quantum realm. The rules of the small. We've gone from the predictable world of falling apples to the bizarre reality of warped space-time. We've seen that the rules don't break, they just reveal deeper truths. But the singularity in a black hole is a different kind of beast. It's where the universe of the large collides with the universe of the small. To understand this collision, we have to meet the other set of rules. Welcome to the quantum world. Down here, solid objects dissolve into a sea of probabilities, and particles act in ways that defy all common sense. One of the foundational rules is Heisenberg's uncertainty principle. It says there's a hard limit to what you can know about a particle. The more precisely you know where a particle is, the less precisely you can know where it's going, and vice versa. This isn't about having bad measuring tools. The uncertainty is baked into reality itself. A particle like an electron doesn't have a single, definite position and momentum at the same time. It exists in a fuzzy cloud of possibilities. You can think of it like reality having a fundamental pixel size. You can't see details smaller than that, not because your camera isn't good enough, but because the information simply doesn't exist in a sharper form. Then there are the laws of thermodynamics, which are like the universe's non-negotiable accountants. The first law is simple. Energy can't be created or destroyed, only changed from one form to another. The universe's energy budget is fixed. The second law is even more profound. It introduces us to entropy, a measure of disorder. The second law says that the total disorder in the universe can never go down, it almost always goes up. This is why a scrambled egg never unscrambles itself and a drop of ink always spreads out in water. Things naturally fall apart. This law is responsible for the arrow of time, the reason we experience life moving forward. A universe without growing entropy would be a universe without change, stuck in a frozen moment forever. Finally, The third law says that as you get closer to absolute zero, the coldest possible temperature entropy approaches a minimum. You can never actually reach absolute zero, because that would mean all motion has stopped, which would violate the uncertainty principle. If a particle were perfectly still, you'd know its momentum perfectly, it's zero. Which means you could have no idea where it is. These quantum and thermodynamic rules are just as rigid as relativity. They aren't suggestions. The uncertainty principle keeps atoms from collapsing. Thermodynamics governs every engine, every star, and every chemical reaction that keeps us alive. So now you have these two incredible rulebooks. On one side, general relativity, a deterministic theory of smooth, curved spacetime. On the other, quantum mechanics, a probabilistic theory of a fuzzy, uncertain world. Both have passed every single test we've thrown at them in their own realms. But at the event horizon of a black hole, their realms collide. And they don't play nicely. This is the heart of the black hole information paradox. Unifying the rules, the grand puzzle. We've arrived at the final frontier of physics. We're standing at the edge of a black hole, where our two greatest theories of the universe, general relativity and quantum mechanics, go to war. So here's the showdown. A sacred rule of quantum mechanics is that information can never be destroyed. You can burn a book, but all the information about what made it a book is still there, encoded in the smoke, the ash, and the heat. It's scrambled, but if you could collect every single particle, you could theoretically piece it back together. The information is conserved. This is non-negotiable. Now, throw that book into a black hole. According to general relativity, it crosses the event horizon, gets crushed at the singularity, and its information is gone from our universe forever. Simple. Case closed. Or so we thought. In the 1970s, Stephen Hawking did something brilliant. He applied quantum mechanics to the edge of a black hole. And he found that, due to quantum weirdness, black holes aren't perfectly black. They glow. They leak a faint trickle of particles, now known as Hawking radiation. This radiation means the black hole is slowly losing mass. And over an absurdly long time, it will completely evaporate and disappear. And here's the paradox. Hawking's original math suggested this radiation is totally random. It contains zero information about what fell in. So, when the black hole vanishes, the information about the book we threw in seems to have vanished with it, completely violating that sacred quantum rule. We have a heavyweight clash. General relativity says the information is lost. Quantum mechanics says it must be saved. Which one gives? Does one of our pillar theories of reality finally crack? This question has driven a massive hunt for a single, unified theory of quantum gravity. And the proposed solutions are wild. One idea is that the information isn't lost. It's just encoded in the Hawking radiation in an incredibly scrambled way. It might look random, but if you could collect every particle for trillions of years, you could decode it and get the book back. A more radical idea is the holographic principle. It suggests that all the information about what falls into a black hole never really goes inside. Instead, it gets smeared out and stored on the two-dimensional surface of the event horizon, like a hologram. From our perspective, the book gets flattened, encoded onto the surface, and its information is slowly radiated back out into space. We don't know which idea is right yet. But here's the amazing part. In every single one of these mind-bending solutions, the universe itself doesn't break. The paradox isn't solved by throwing out one theory or the other. It's solved by finding a deeper, more sophisticated rule that unites them both. The apparent conflict is just a seam where our descriptions of reality meet, and we're just now learning how to stitch them together. We started with a simple question. What happens when you push the universe's rules to their limits? We went from Newton's predictable world to Einstein's stretchy, bendy spacetime. We journeyed to the edge of a black hole, where reality itself seems to tear, and we dove into the fuzzy, uncertain quantum world. And at every single step, what looked like a crack in the rules was just a doorway to a deeper truth. Newton wasn't broken by Einstein. He was just one chapter in a much bigger book. General relativity isn't broken by a singularity. It's just a signpost pointing the way to the next chapter on quantum gravity. The universe isn't trapped by its rules. It's built from them. These laws, the cosmic speed limit, the arrow of time, quantum uncertainty, the conservation of information, aren't a prison. They are the architectural blueprints for reality. Without a speed limit, there would be no cause and effect, only chaos. Without entropy, there would be no change, no evolution, no life. Without quantum uncertainty, atoms would collapse and nothing could exist. These limits aren't flaws. They're the features that make everything we know and love possible. The cosmos is a self-contained, self-regulating system, bound by its own inescapable logic. The rules don't shatter at the extremes. It's at the extremes that they show us what they're really made of, handing off authority from one law to the next in a perfect, unbroken chain of command. The universe will always be trapped inside its own rules. And that is a very, very good thing. Because we are living proof that this system works. The hunt for these ultimate rules is what drives science. This clash between gravity and the quantum world is the great puzzle of our time, and solving it could change everything. If you want to keep exploring these mysteries with us, make sure to subscribe. And now I have a question for you. Which of the universe's unbreakable rules do you find the most fascinating? Let me know in the comments below. Thanks for watching.